Ladies and gentlemen, sorry for the crowd is still waiting out there or coming from somewhere, but you guys have to remember this is Miami time. Okay, no matter when we set the time to start, unfortunately, it's not everybody's time to get started. But while we're going to get started, because we do have a full program, I'd like to again invite, thank you for coming. And on behalf of my colleague, Dr. Daniel Berg, distinguished research professor and a fellow member of the National Academy of Engineering, and myself, I'd like to welcome you all to this joint regional meeting of the National Academies of Engineering and Medicine. Dan and I feel especially honored to have been asked for a third time to organize a regional NAE meeting. Moreover, it is a unique symposium in that it is being co-sponsored by two of the three national academies, engineering and medicine. We have entitled the symposium A Critical Partnership in Technobiology. By technobiology, we mean the application of engineering or technology to biology or medicine. As you are all aware, the US healthcare system needs to become more efficient and more effective, that is, more productive. Just as engineering has made the manufacturing of goods and the delivery of services more productive, it must now focus its talents on healthcare. Indeed, the time is ripe for more technobiology breakthroughs, and I am proud to say that the University of Miami is a leader in this effort, as reflected by this symposium. In fact, here at UM, the College of Engineering and the Miller School of Medicine are successfully collaborating on a range of efforts in technobiology, some of which are addressed in this symposium. On the other hand, it should also be noted that UM is likewise pursuing applications in biotechnology, or the application of biology to technology, including, for example, neural networks, which concern how neurons network and function to help model complex relationships between inputs and outputs of a large data set. So coming back to today's focus on technobiology, we will hear presentations on critical biomaterials that have helped to establish the fields of interventional cardiology and interventional glaucoma, on polymer structures and their impact on biofunctional surfaces, and on drug discovery by employing organs on a chip. Let me now introduce the other 6 individuals up here in the dais. As indicated in your trifold program, they will provide some additional introductory remarks. However, before I do so, I would like to acknowledge the presence of 2 other individuals who have helped us with today's program. The first is Dr. Julio Frank, the current president of UM and a member of the National Academy of Medicine. He will be joining us a little later when he shares a discussion of the 3 presentations. The other individual who deserves our recognition and appreciation is Dr. Donna Shalala, a member of the National Academy of Medicine and the former UM president. As some of you may recall, she also moderated our 2010 symposium. Thank you, Donna, and welcome. Now let me commence by saying that it is my distinct pleasure to introduce the President of the National Academy of Engineering, Dr. Dan Moult. He held a number of faculty administrative, it's all right, you can stand up. He held a number of faculty and administrative positions at UC Berkeley before becoming president of the University of Maryland. In 2013, he was elected president of the National Academy of Engineering. Ladies and gentlemen, President Moult.
Thank you very much, Jim. Thank you very much. Well, I only have 4 minutes, so I didn't want to use too many seconds walking up here. Jim, thank you very much, and thank Dan Berg also, the 2 of you, for putting this very important symposium together. The Academy calls on its members to create these regional meeting symposia, and we're very, very fortunate to have Jim and Dan take this on, and it's a great pleasure to be here. There's these regional meetings happen regularly at the Academy. In fact, this is the 18th year we've had regional meetings. And they really rely on universities and industries to put together these programs for us and essentially bring the Academy out to the nation. And so this happens to be, of course, the university one. It's the first one of 5 that are scheduled this year. They have 5 a year around the country. But as Jim suggested, this one is very special. And I emphasize the very part of this. This is the first regional meeting that's ever been put together that actually is a joint meeting with the National Academy of Medicine and the National Academy of Engineering. And of course, the title of this meeting is Engineering and Medicine, a Critical Partnership in Technobiology. And boy, that is definitely true. This is a period between engineering and medicine that has actually been going on for decades. It's been going on a very long time. But suddenly it's turned a corner at this point where now engineering and medicine realize that their futures independently depend on their partnership together, as a matter of fact. So this is a different phase. From this point on, you can expect to see this around the country and around the world. I'm very eager to hear about the speeches today, the presentations at the symposium from truly distinguished experts on this topic. I mean, you would have to go a long way to hear better speakers on this topic than you'll hear today. So I thank the speakers. I thank Jim and Dan for putting this program together, and I thank the partnership with the Institute of Medicine for bringing this all together for all of us. So thanks, Will, and I think I've lasted under my 4 minutes. Thank you very much.
Sorry to have you walk around a little dangerous corner here, but we really don't have too much room up here. It'll get easier because the next set of people will be just 4, so we'll have some space. So it is now my pleasure to introduce the National Academy of Medicine Home Secretary, Dr. Jane Henney. She has had a distinguished career in health policy, and she is currently the Dean of the School of Medicine's Advisory Board at the University of Kansas. Ladies and gentlemen, Dean Henney.
Well, thank you, and I will add my thanks to you, Jim and Dan, for hosting us and all the hard work that it takes to put such a symposium together. I so appreciate your efforts in this regard. And as I look out at the audience, I particularly want to thank you for inviting a number of students to this, because they really are our future in terms of discoveries yet to come that will truly change our worlds. I bring you greetings on behalf of the National Academy of Medicine. Victor Zhao, our president, is winging his way to Singapore, so couldn't be with you today. So I am his poor substitute, but nevertheless, my greetings are sincere. I bring you welcome from him. I will also bring another message from another person that I worked for many years, and that is your former president, Donna Shalala, who informed me at noon that she's giving an exam in this room at 5 o'clock. And so you are all to vanish by 4:45, lest you be run over by all of these eager students who cannot wait to tell her how smart they are. So there you have a welcome and an end. But I would also echo Dan's words in terms of the excitement of what's already been accomplished between the partnership of health and engineering. We know that many medical devices currently at our disposal, bringing the discipline of engineering into the CDC, and those engineers at CDC that helped really were involved in malaria control efforts in standing water. We know that systems engineering has also played already a pivotal role in redesigning, re-engineering many aspects of our current healthcare system. But what we're most excited about is what is yet to come. And I think that is the subject that will be brought to us by many of the speakers that we'll hear from this afternoon. We, in the work of the Academy, still take, in terms of our consensus studies and many of our projects, this joint partnership quite seriously. Our reports on building a better delivery system, a new engineering healthcare partnership that was published in 2005, a long time ago that is, and smart vaccines published in 2015, I think are really reflective of how the academies can incorporate both the disciplines of health and medicine and all of those sub-disciplines that engineering and medicine reflect. So I look forward to today and what is yet to come. Thank you so much.
Thank you, Dr. Henney. Our next speaker is our own Executive Vice President and Provost, Dr. Jeffrey Dirk. He joined us in July 2017. He was previously the Dean of the School of Engineering at the Case Western Reserve University, where he was also the founding director of the Case Center for Imaging Research. Thus, he himself has been clearly involved in the imaging area of technobiology. Provost Dirk.
So on behalf of the University of Miami, I want to welcome everybody here today. And I was looking out in the audience, I started thinking about what is it that brings a director from a center of computational science, a leader in civil engineering in Johnson & Johnson, other leaders in Johnson & Johnson, our world-renowned Bascom-Palmer Eye Institute here together. It almost sounds like the setup to a joke, doesn't it? You know, the great thing about events like this is it does bring people together with the opportunity to answer, I don't know what brought us together, but we're excited about what might come from this. And it is that idea of the integration of technology and biology that really offers all of us a great opportunity to imagine what will come next. In my case, for example, all of my research was in magnetic resonance imaging, and many times technology has been implicated for the rising costs of healthcare. And I think what many of us recognize is we have great opportunities to not only demonstrate how, in fact, the integration of technology and biology actually bring costs down, but also pave the way fundamentally for important advances to the patients, because that's essentially why we're all here today, is to find those great opportunities. So I know that with my colleague Ed Abraham and I, who are two of the leaders at the university, we draw on the foundations established by Donna Shalala and others to really make sure the University of Miami is a welcoming place for the integration of those two disciplines. And we really want to thank all of you for being here today and participating in what we hope to be the start of continued robust discussions on these topics. So thank you all for being here, and we're really grateful for your attention today.
Thank you, Edward Abraham. He is also the CEO of UHealth. Previously, he was Dean of the Wake Forest School of Medicine. Dr. Abraham is an internationally renowned pulmonary and critical care physician. Dr. Abraham.
I'll add my welcome to everyone as well. The provost talked about how important integration across the university is in terms of engineering and medicine in the greater whole. And let me just say something about two specific examples. The School of Medicine recently underwent an intensive strategic planning process for research efforts. It involved about 300 of our faculty members. And through this, a number of areas where we have close interactions were called out. So we have a Center for Nanotechnology that was funded with a $7.5 million grant, an award from the John T. McDonald Foundation, and includes faculty from medicine, engineering, and science, and involves the establishment of a unique nanofabrication facility. This was called out as one of our important bridging technologies. informatics, handling large data sets. The Center for Computational Science also was called out as important in terms of our research efforts. The provost and others have mentioned our efforts in ophthalmology as well. Clearly, how we approach neurosciences, sensory research involving sensory programs has also been important. So in a limited number of important areas where we have high-performing teams that can become absolutely preeminent through these interactions, our research strategic plan is focusing on those areas. It's incredibly important for us to have these synergistic relationships in team science, reaching across this great university, taking advantage of the intellectual assets that we have. It's really a major priority for us going forward. So the fact that we're having this symposium where we bring together multiple different disciplines and groups and think about how we can work together, how we can take advantage of strengths and actually get that true multiplicative effect through those interactions is critically important for us in terms of moving forward, in terms of our vision for preeminence, but also our vision for having highly impactful and innovative programs. So I'm very anxious, looking forward to the kind of interactions that will occur during this symposium. And again, just want to welcome all of you here. Thank you.
Thank you, Dean. I have to remind myself that we were planning all kinds of things of how to handle. There was supposed to be 350 people here for this symposium by Eventbrite. I mean, you register, and lo and behold, I don't think we've filled this auditorium, which is only 300. So 50 are still out there, but I think there's more than 50 to come. So sorry about we thinking that we're going to need more space and more this and that, but we really are happy, though, that you are here. And the next person I'd like to introduce is Dr. Jean-Pierre Bardet, the Dean of the College of Engineering. He was previously on the Civil Engineering faculty at the University of Southern California before becoming Dean of the University of Texas in Arlington. Dean Bardet.
Thank you, Jim. So welcome to this event. And on behalf of the College of Engineering, it's really a pleasure to host you here. I want to thank the member of the National Academy of Engineering and Medicine for leading the conversation. In particular, I would like to thank Jim Tien, and Dan Abrams, who really have masterminded this event. I want to thank also the guest speakers, and you'll find out them to be extremely rich in the message they're going to deliver. Matt Tyrrell from the University of Chicago, Len Pinchak, alumni, and also one of our professors in the biomedical engineering department, and Ashutosh Agarwal, an assistant professor in the same department, the biomedical engineering. Now, two adjectives came to my mind when we organized this meeting, and it was really the adjectives were timely and convergent. Now, timely because this event takes place at UM at the time when UM is investing in science and engineering. You heard certainly about the STEM at UM. A new building is under construction, a building, the Frost Building for Science and Engineering. To the groundbreaking, I think, ceremony is supposed to be on May 3rd. Then there is also the Frost Institute for Chemistry and Molecular Science, which is contemplated. And we are actually presently looking for a director of this institute. And so we have Matt here, Matt Tyrrell, who is actually the director of the Institute for Molecular Engineering at the University of Chicago. So imagine the kind of things we can learn from Matt to guide us into this new endeavor with our Frost Institute for Chemistry and Molecular Science. Now, the second adjective is convergent. And this event, I believe, is quite convergent. Convergent, of course, between medicine and engineering. And convergence is something more precise and interdisciplinary, multidisciplinary, interdisciplinary. We heard these terms over and over. Convergence is in the sense of Mike Rocco of the National Science Foundation, where basically you have various disciplines which fuse together, driven by a common mission, a common vision, and they fuse around grassroots opportunities, not institutional top-down kind of mandates. Now, two examples. The first one I can think of is actually the field of biomedical engineering. Biomedical came up with a fusion from electrical engineering, mechanical engineering, biology, and suddenly there was a new field, and medicine, of course, all right? So we are lucky, most of our actually biomedical engineers have a joint appointment in the medical school. Now, another example is in your pocket, an example of convergence, your cell phone. This is a convergent device where we bring together the GPS, the battery, the databases, the VLSIs, all kind of technologies. And on this platform, we're going to build telemedicine. So a lot of convergence here. Now, we have a few partnerships at University of Miami which are already evolving toward convergence. You heard already Bionium, led by Richard Coty. These nanofabrications, where we can fabricate sensors to sense tiny, minute quantity of cells reactions. And of course, something we are very proud about, and it's the Johnson & Johnson 3D Centers of Excellence, 3D Printing Centers of Excellence, a collaboration between Johnson & Johnson and the College of Engineering. Now, I don't know if you can see it, but I hold in my hands, not a crystal ball, that would be nice, but a titanium ball printed in the center. And that could be a human eye in the future. I coat it, put some sensors, and maybe we'll be able to restore vision to people. And so the idea is clear. In the Johnson & Johnson, we are doing personalized healthcare. The idea is to go from the MRI imaging to the body parts, and that would be manufactured at the hospital. Every hospital should be able to manufacture body parts and supply these to the surgeon. Now you're thinking about more precision, more speed, more organic shapes, more savings. And so this, I believe, is an example of a future convergence. Now, these are my two adjectives, timely and convergent. So I look forward to this meeting, and I'm looking forward to stimulating discussions on the timely convergence of medicine and engineering at University of Miami and beyond. Thank you.
Thank you, JP. So finally, I'd like to introduce my close colleague, Dr. Daniel Berg. He was a technical director at Westinghouse before pursuing an academic career as Dean and Provost at Carnegie Mellon University, as Provost, President, and Institute Professor at Rensselaer Polytechnic Institute, and now as Distinguished Research Professor at College of Engineering. Dr. Berg.
Thanks.
Could I just disturb you
If
a
it's
minute?
about me,
Why don't
Jim,
we
you
all
can go
get
on.
off, because right after this is the presentations. And it'd be difficult to look the other way.
That's called stage engineering.
Thanks, Dr. Tian. Good afternoon, ladies and gentlemen. Buenas tardes. Before I introduce the three symposium presenters and discussants and the symposium moderator, UN President Julio Frank, perfect timing. I would like to make some introductory remarks. Our program committee selected 3 special speakers. They each have a theme, but combined they exemplify a generic approach in the development of translational technology. The speakers, each in their own right, have created fundamental knowledge and have done so in areas of societal need, while at the same time enabling the utilization of their created knowledge. Thus, they have been using a feedback loop of asking fundamental questions, developing new knowledge, and understanding in areas ripe for utilization. This process of creating this fundamental knowledge in areas of need and utilization is referred to often as the Pasteur quadrant, after Louis Pasteur, eminently successful at solving major problems in technobiology. The Pasteur approach, in particular, is pertinent to what we're trying to achieve here at the university as we engage in a range of efforts in science, applied science, and engineering. Interestingly, Pasteur himself, a very successful technobiologist, was famous for several innovative successes. We all know that pasteurization makes milk potable. Less well known is that he was commissioned to save people who were bitten by rabid dogs. In doing so, he succeeded to develop an appropriate vaccine and validated the principles of vaccination. But I think the most creative discovery of intellectual importance was when he was commissioned to help the wine producers in France. He did so by discovering principles of microbial fermentation. But more importantly, he employed the best technology at the time, a pair of tweezers. He meticulously divided crystals that had precipitated in wine, crystals of potassium tartrate that had precipitated in the wine. The selection criteria for his picking the crystals out, because there were 2 types, one type being the mirror image of the other. Lo and behold, the crystals that he got in the 2 piles, the mirror images of each other, behaved differently while in solution. One pile rotated light to the left, the other pile rotated light to the right, levo, dextro. When mixed in solution and put together, the rotations were balanced out. Miraculous stuff, that the same chemical entity, chemical composition, had different physical properties. His optical observation led to basic understanding of the different structural impact of molecules of the same chemical makeup. Asymmetry is a fundamental characteristic of life. It underscores the efficacy of creating knowledge and understanding in needs of societal need, and then evolving the ability to solve the problem. Pasteur also illustrated the power of the systems engineering approach, but that's another story. In sum, the Pasteur quadrant of developing fundamental knowledge in areas of societal need and utilization of that knowledge is very much embedded in the underlying theme of the 3 symposium speakers. I'll begin the symposium proceedings by introducing the individual speakers in order of their talks. The first presenter is Dr. Leonard Pinchuk. He is entrepreneur extraordinaire. Bonjour. He's CEO of Novia. You can start coming up, Len. And he's Distinguished Research Professor of Biomedical Engineering. His focus concerns key biomaterials that have helped establish the fields of interventional cardiology and interventional glaucoma. Please welcome Dr. Pinchuk.
There are people out here. Thank you very much, Dean Chen, Professor Berg, for inviting me to talk here. And thank you all of the distinguished people who are here. If I had known you were coming, I would have gotten a lot more nervous. Now, the slides I have here are not really for you, they're for me, so I know what I'm talking about, but I don't have a monitor, so I'm gonna angle myself. Okay, so if this works, which it doesn't, there you go. Okay, I'm gonna pop in and out of entrepreneurship, and in and out of engineering, in and out of chemistry. They're all very important in getting these things done. And the most common question, we're gonna start with entrepreneurship, is that people ask me is, when do you start your company? And I remember this Bob Dylan lyric, when you've got nothing to lose. So if you don't have kids, and if your kids are really young, you can do that, or if they're really old. I formed my first company when my kids were really young, and my partner formed his when his kids graduated from college. Best when you can survive a year without salary, best to pair up with a sophisticated CEO and board of directors. I'll talk a little bit about that more. Do you leave college to start your own company? Startup successes are low probability, best to finish your degree. Whatever you do, don't burn bridges behind you, because you're gonna need the references. You need them to raise money. And also, there's a good chance you have to go back to your previous job. And the main cause of small company failure is isolation. You think you know what you're doing, but you don't. You need to surround yourself with people in the know. So with that in mind, and the importance of resourcefulness, I just want to mention that's me, and you have John Martin in the audience there if you want to wave, John. He's one of these people you want to surround yourself with. John is the type of person you can, first, if he doesn't talk you out of your idea, he'll have a prototype made within 24 hours. Resourcefulness. One day when my wife wasn't present, I converted our shower into a fume hood because we had to work with chemicals, and we just couldn't do it on an open bench. And we ran that way for a while. So we started off, I was a co-founder of Corvita Corporation, and our goal was to develop coronary bypass grafts to bypass obstructions in the heart. And we used what's called a polyether urethane because the FDA had cleared that for use as insulators on pacemaker leads. And what we did, this doesn't always change. Come on. Okay, we'll try it again. So what we did is we spun fibers, and this is a spinneret on a rotating, that's spinning fibers onto a rotating mandrel. So these are 30 fibers coming down, and the spinneret's going back and forth hundreds of times, and we build up a meshwork on here. So one of the things us engineers have to do is not only design the processes, but we have to build the machinery to do it. And this is actually a lot of fun, and this is where you try and find more John Martins to help you with that. And if you take the mesh off the mandrel, it looks like this. And if you look at a scanning electron micrograph of it, this diagonal here is a human hair. So these fibers are about 20 microns, and they're oscillating each heartbeat. They're expanding and contracting. And we thought it would be a great product for a standalone company because we're going to eliminate the use of saphenous vein for coronary bypass. So we implanted a bunch of them. We left, we were working at Cordis at the time. We left to form Corvita. And we did explants, and we found 100% of them failed, and they were all degraded. All these fibers began to show cracking. So the pessimist sees the difficulty in every opportunity, the optimist, the opportunity in every difficulty. So this is important because you have to be an optimist. So I said, let's get Cordis into angioplasty, and let's develop our own implantable material. So let's look at the origin of biomaterials. Really, it was physicians trying to solve problems. So the artificial heart was one of the first ones, where they just took a woman's girdle and they cut it up into a diaphragm that can oscillate back and forth. And this became the membrane for the artificial heart. William Kolb, when he did the dialyzer, he just bought casings from sausage stuffings, and he ran blood through it in a water bath, and he was able to dialyze blood. Then bifurcated aortas came from pantyhose knitting machines and weaving machines. And the insulators on wires, the original inventor of silicon rubber was General Electric. But Dow Corning beat them to the breast implant, and that was probably the biggest mistake they ever made in their history, because as you all know, they were sued for $3 or $4 billion. And polyurethanes also, for insulators, came from mattress stuffing and brush bristles. So I'm going to talk a little bit of chemistry here because it's important. This is a diacid, and R is a number of carbons that can be 1 to whatever you want, we'll say 10. And you take what's called the diamine, which is in amine groups, and you have another R, which could be carbons, could be 10, 5, 6. Amines react with acids, and they give you this link over here, which is an amide linkage. Now, the acid can react with this amine, and this amine can react with this acid. So this is one unit, and it's a unit in Latin is a mer. If it reacts again, it's a dimer. If it reacts a third time, it's a trimer. And if it reacts hundreds of times, it's a polymer. So that's what polymer is, polymer. And you maintain the amide group. So this was synthetic silk that was developed in the 1930s at DuPont by Carruthers. And he did the work, according to DuPont folklore, between his labs in New York and his lab in London, and it became known as nylon. All right. Now, because you have your R's and your R primes, you have different forms of nylon. So if you have nylon 6 carbons in the carboxylic side and 6 in the amine side, you have your moldable gears and other machine parts. We all heard nylons were stockings because they're made from nylon. That was nylon 4,4. You have the casings of power tools is nylon 6. Nylon string guitars, nylon 11. Then you have this really peculiar unknown nylon called nylon 12. And this is where the fun starts if you're an organic chemist. So nylon 12 has 12 carbons in a ring, and you have your amide group up there. But those of you who've taken organic chemistry, you know that loops really don't exist in nature. If you remember from cyclohexane, you have your boat form and your chair form. So you're not going to see a 12-member loop, but you're going to see a twisted molecule that looks like this. So the dark lines are coming out of the page. So let's take this twisted molecule, and if this clicker works. And in the presence of heat, you can open up the ring. So let's put two of them together, and here you have your amine reacting with your acid. And you form a polymer of nylon 12. So what makes this interesting is that if you take this twisted ring, and we're going to make a tube out of it. Well, first, if you stretch it, you see it elongates, and it doesn't come back. So you take an extruded tube called a parison, and you pull it. These are the rings that are opening now. And it's stable like that. It's not like a rubber band. It's not going to pop back. So you've axially oriented. To biaxially oriented, in other words, to orient in the other direction, what we do is we can put in a fluid. It could be water, it could be air, normally done in a heated mold so you can maintain the shape. I couldn't grow it bigger than this, it would have popped because it's not in a mold. But this is the principle. And then you can deflate it, and what we did is we stretched it and blew it twice. It was called double stretch blow molding nylon 12. So this became one of the first materials for an angioplasty balloon. And for those of you who don't know angioplasty, it's any tube that enters the body is called a catheter if it's not a needle. And then you take a balloon, you blow it up, And although it looks like it's the footprint in the snow, and if there's any students here who don't know what snow is, come see me after. And that's what it's supposed to do. But what makes this interesting is the thickness of these membranes are 10 microns. And then if you think of it in reference to saran wrap is about 12 to 14 microns. So it's thinner than saran wrap, but it can hold 300 psi of pressure. While we're at it, saran wrap was named after the daughter of the inventor. The daughter's name was Sarah Ann, and that became saran wrap. That's where that came from. So the eureka moment was basically, we went to Cordis, and they were trying to make balloons of a material called polyester terephthalate. We were able to put our balloon through the lumen of theirs and blow it up larger. And they said they have to own this. And again, we had to build the machinery to make these things, and we only build it to make, maybe tens to hundreds at a time, but eventually they have to make tens of thousands at a time. So a lot of engineering goes into this. And there's John again. And we had to make machines that made these things blowable up in the heart leaflets of all different sizes. So there were 19 issued US patents, and the lawyers extended it from 1987 to 2013. It was the first angio balloon catheter to be maneuvered to the back of the heart from an opening in the femoral artery or in the arm, in the radial artery. So it really, it became the #1 seller in every major country in the world, and the only balloon catheter currently used. Now the patent's expired, no one else, everyone uses nylon 12. There's no other materials used. So we guessed right back in 1987. And it's used for percutaneous luminal coronary angioplasty in the legs and stents, cutting balloons, drug-eluting stent, drug-coated balloon, kyphoplasty. They all rely on this nylon 12 technology. And according to Evercore, there's over 100 million procedures that are done now with over $100 billion in revenue. So it's really one of the largest life-saving devices that there is. And this provided the seed money and the credibility to continue Corvita. We're now able to get ourselves financed. All right, so what happened? It's not a commercial break. And I found this easier if you empty this bottle. If you take this bottle, well, what happened is DuPont sued us. He said, your balloon catheters are infringing the soda bottle patents. And if you take a soda bottle and you step in it, you get what's called winging, where the legs are crystalline. And this is one of the things that we fought with them, that the whole key to making an angioplasty catheter work is really the legs. So here we have, I don't know if you can see it well, but the balloon's inflating. And these are the legs. And you can go up again to 300 psi. You can step on these things. In fact, you can drive over them with a car. They're really, really tough. But importantly, when you deflate it, you can pull it back into the guiding catheter that you used to bring it there. Also, when stents became available, you can inflate a stent, then you can deflate it and pull it out without dragging the stent with you. And this is one of the reasons why they became important. We then went on and developed one of the first coronary stents. And we sold that to Cordis, but Johnson & Johnson bought them, and they shelved it in favor of the Palmas shot stent, which was shelved in favor of the Fischel stent, which President Moat knows about. But it later showed up now as the stents used by Medtronic in the Endeavor and the Resolute. So there's still, these stents are one of the most commonly used stents now. Okay, so we'll check that one off. So let's develop our own implantable biomaterial. So at first we fixed the polyurethanes. We got rid of the ether group, which was the labile area, replaced it with a carbonate group. This became Bionate, which is one of the largest products sold by a company called DSM, a Dutch consortium who provides polymers to the industry. And it looked pretty good. But the problem is, we learned at that time, if we're going to go after a coronary graft, you need about 5 years worth of data before the FDA will allow it, or the surgeons will put it in, because if it fails, it's catastrophic. So before Match.com started, we developed our own and we introduced a stent to a graft. So this is a stent. It's made out of a material called Elgiloy, which is from Elgin, Indiana, which came from the Elgin watch, which was the mainspring on the watch. So it was braided, and we added that to our liners, which I showed you earlier, and we ended up with a stent graft. And the way that works is you can take these spring openings that are attached to the fibers and you can compress them down into a catheter, and then you can deploy it. You can push it out and they pop open. And that's the stent graft. So this was our first case. It was a lady who was in a car accident, and her aorta was perforated and her abdomen was full of blood, and they couldn't go in surgically. But they decided if they can go in through the leg artery, they may be able to fix the hole internally. So they deployed our stent graft in there, and here you see blood flow going through the wall. And with time, it begins to diminish as the blood clogs in the wall. And this lady was able to walk out of the operating room after 1 or 2 days in the hospital. She would have died without it. So this is one of the first uses of the stent graft. Not much of a market in trauma, so we had to look at where there is a market, and abdominal aortic aneurysms is the 13th cause of death. So that's where the abdominal aorta is. So what we did is we developed a bifurcated trunk that you assemble it in the body. So here you have 2 legs in a stent graft. Then you go into each leg with the stent graft, and you deploy that in there. And you do the same in the second leg. And now blood stays inside this conduit and eliminates the pressure on the aneurysm, so the aneurysm doesn't grow. And there's been over 1 million procedures done so far with this. It's really about half of aortic aneurysms are fixed now endoluminally without having to go through an open surgical procedure. And this is what it looks like under X-ray. And since we did ours, which is in here, there's been a myriad of different competitors that came out. And this is common in medical device. So we were successful. We went public on the NASDAQ in 1994. We were acquired by Pfizer Schneider in 1996 for $85 million. That's a major lifestyle change for us. Boston Scientific acquired Pfizer Schneider in 1998. But what bothered me, there was a slow degradation. Most of the time the fibers look good, but occasionally you see this cracking. And again, as a former organic chemist, you say, well, why are you putting in urethane groups? So I didn't want to put a Band-Aid on this. So we need a new biomaterial that won't degrade. And furthermore, what's happening is when your material flexes, these granulocytes or macrophages lay down on the material. That's what they like to do, and they spread out. And then they secrete superoxide hydrogen ion. The pH is going to go down to 1. Small molecules come off that nobody wants to talk about. But the material begins to embrittle. Remember that term, embrittle? Crack and degrade. And this is the picture I showed you early on. This is what was happening with the polyurethane. Oh, shoot. Okay, so I left out the fact that it attracts all these granulocytes, and you see polymorphinucleoleucocytes and giant cells and phagocytosis. So the hypothesis was the surface tension characteristics of a polymer dictate the acute foreign body reaction. So what happens in the first few hours is a function of the surface tension. The long-term foreign body reaction is a function of the inertness and cleanliness of the polymer. So when we hypothesized that if you could make a polymer that's ultra-pure, totally inert, and matches the compliance, in other words, the flexibility of tissue, it may not elicit a foreign body reaction. So this is what we set out to do. And the strategy was simple for an organic chemist. You had to eliminate every bond that's cleavable. So we had to get rid of ethers, esters, amides, urethanes, ureas, carbonates, and I'll talk about these carbon-carbon bonds. But these are all the major bonds used in just about every polymer that we know of. So let's look at a simple polymer. The most simplest is polyethylene. It's just linear carbon, and I've left out the hydrogens. And for nomenclature reasons, carbon connected to one is called a primary. Carbon connected to 2 carbons is called a secondary. So you bring out your macrophages, they secrete their superoxide hydrogen ion, and you can form these free radicals on the backbone. This is an oxidation reaction, and with time they begin to conjugate. In other words, you get double bonds on every second carbon. That's its lowest energy form. So if you think of a carbon-carbon bond as 2 pieces of wood, 2 planks, you can rotate the planks if you had 1 nail through it, which is like 1 bond. Put 2 nails through it, they can't rotate. So this manifests as embrittlement. So polyethylene will embrittle with time, and many people have written about that because polyethylene used to be used as liners on acetabular joints. If you go to the more complicated, but still simple polymer called polypropylene, you now have your secondary carbons and your tertiary carbons. Bring out your macrophages. Still get a free radical in the backbone, and you can still conjugate and form the double bonds. So polypropylene will embrittle. And again, lots of people have written about that. All right, so let's go now to polyisobutylene, where you have the quaternary carbon. Here you have 4 carbons around a carbon. Bring out your macrophages. Maybe you can get a free radical to form on the backbone, but chances are it's going to be blocked by the methyl groups over here. But this reaction will never progress to conjugation, to double bonds. The reason is carbon cannot have 5 bonds. It can only have 4. So the reaction stops here. So polyisobutylene is a very, very stable material. And this is one of the, oh yeah, and if you don't oxidize all of these species of granulocytes, they tend to disappear. Okay, so we have a lab in West Kendall. And what we do is we drop the temperature to -80. We make our own molecules here, and we grow it by condensing in isobutylene gas. And we grow this, this continuation of, if you note, the quaternary carbon to the secondary carbon, quaternary, et cetera. So this is polyisobutylene, which is kind of like chewing gum. If you want to convert chewing gum to an elastomer, to a stretchy material, you either have to vulcanize it and cross-link it, or you have to put in meltable crosslinks. And we put in meltable crosslinks. If you take 800 of these units, meltable crosslinks are glasses. And typical glasses are plexiglass, polystyrene, polycarbonate. But we use polystyrene. And we form this polymer. And I won't talk about this here. But it's called, we have a block of polystyrene, a block of polyisobutylene, a block of styrene. So it's polystyrene, block isobutylene, block styrene, or SIBs. And here are the blocks of your glassy segments holding the rubbery strands together. So if you take, this is just the concentrated nitric acid. It's the highest concentration you can buy without a military license. And you put SIBs into it. It's just a film of SIBs. It's probably going to be hard to see here. But we're going to compare its ability to be destroyed in strong acid and strong oxidizing agent versus silicone, which is used in the body everywhere. And you're going to see with silicone, it turns back to sand, because silicone is formed from sand. In strong acid, it reverts back. So you're going to see that piece just break off, which it just did. Dacron, which is used in vascular grafts, we're just going to put a little swab in there, and you see within seconds it's gone. And that's because it's porous, and it has ester groups, which are cleavable. And our polyurethane I played with is a very vigorous reaction, disappears in seconds. But you can leave SIBs in there as long as you want, and it's not going to get destroyed. So other companies such as Medtronic, Boston Scientific, they've all now identified SIBs as being the most bioinert, stretchable material they've ever tested. So it's become the standard to beat, and they haven't beat it yet. This just is a curve that says if there's biodegradation, the molecular weight would drop, but it doesn't drop. And we looked at histology for many years. We didn't see any of those granulocytes I talked about earlier. All right, so let's get back to angioplasty. You have a 40% failure rate with balloons blowing up in here. If you put a stent in and you deploy the stent, you drop it to 33%. It's still not a good number. There's a lot of failures. So the question is, what's going on? So if we go back to our little model over here, when you inflate your balloon, what you're doing is traumatizing the cells in the wall. Now, you don't have to be a cardiovascular pathologist to see that these cells are traumatized. You see, they're all unhappy. And what they do when they're unhappy is they multiply. And they form this fibrous web, which becomes a blood clot. And this is the restenosis that occurs, and blood stops flowing. So if you take your bear stand, now actually a lot of people began to realize that it was the proliferation of smooth muscle cells that was causing restenosis, but it was Robert Fischel, again, who did he was the first one to come up with the product. And what he did is he said, let's make the stent radioactive so the cells can't divide. And this is kind of what he did. Now, there was a problem with that. You see, if you're going to work with a radioactive material, the interventional cardiologist who controls the patient has to bring in a radiation oncologist, and he has to split his fee. So us people in industry knew that if we can kick out the radiation oncologist, we'd have a very happy interventional cardiologist. So the race was on who can put a radio-mimic drug. And that's a drug that mimics radiation. And your layman term for radio-mimic drug is a chemo drug. So there were 3 popular chemo drugs, paclitaxel, rapamycin, and mitomycin C, which we use in ophthalmology. So the race was on who can put it on. And so Boston Scientific, who needed a polymer to release an anti-proliferative drug, this is the drug I'm talking about, and the properties had to be, it must conform to the stent and open with it, it must solubilize and release the drug, and it must remain patent when the drug is depleted. A better way of looking at it, and you can try this when you get home tonight, is take your chain off your bicycle and get a nice clean white shirt and put the chain on it. Okay, then take the chain off, and you'll see there's a black mark. So now you've transferred the grease from the chain to the shirt. Now, you can do this underwater. It's still going to transfer because the grease is not soluble in water. So we had to find a drug that was not soluble in water, a carrier that was not soluble in water, and it had to transfer to tissue and have similar properties to tissue so it will transfer. So I was called into, the drug we're using is paclitaxel, but just for time reasons, I'm not going to go through this. But this is the molecule that they used, and all they were missing was a polymer. Now, they called me in, and if you look at the bare stent, these are struts from a stent, it's a coronary artery, and here, this is good. There's blood flowing through here. They called me in because they were testing my polycarbonate urethane, which I showed you earlier, and they found that it occluded 100% of the time. And they tested 20 or so other polymers, and they all occluded. And, well, they blamed it on me, and they said, well, why is your polymer contaminated and causing this problem? And I said, no, it's not contaminated. The more contaminated, the better it works, actually, because it blocks the surface of the urethane. But if you want something that's going to work, you got to try this new SIBS polymer. And I showed them that you're going to see polymorphonucleoleucocytes, so if you blow it up, very easy to identify, there they are. And that was the issue. So now we took a bare stent, coated it with SIBS, and we're now able to go from 100% failure rate to 100% success rate. So this is at 90 days and 180 days. So this became the drug-eluting stent. And what we do is we take SIBS, dissolve it in a solvent, and we take the drug in the same solvent, you spray it onto a stent, and now the drug goes into the wall of the stent, and it just keeps the cells from proliferating. And the failure rate went down to close to 0 at 6 months. It was a night and day difference. And Boston Scientific, when they released it, it was the largest sales product in the history of medicine. It went to $3 billion in the first year. And it's now been in millions of people since 1999. But important to me, oh, by the way, the catheters used to deploy these stents, both Cordis had one now and Boston Scientific, they're all nylon 12 catheters. So it was kind of like neat to watch this. And again, we had to build the machinery to produce SIBS. There was no source of it. We had to figure out how to purify it. So this is part of our job as engineers. So Boston Scientific offered to finance whatever I did as long as I did not compete with them. So being a financial genius, you kind of realize that you only have one heart, but you have two eyes, so you can sell twice as much product. So this is what kind of got us towards ophthalmology. But not right away. First we formed the Novia, because Novia became the shell company. And it had its ups and downs, and the biggie here was almost 3 years after we did that, they changed the light bulb. I had to get all my business cards reprinted. And a few years later, they changed it again to the LED. And for those of you who start companies, you need a mission statement. And this is ours. Yeah, people have to know what you do. All right, so very fortunate, and this is where partnerships are important. Bascom Palmer Eye Institute is around the corner. And I had known some people there. I helped with the formulations of silicones used in vitrectomy when I was a student, and they've been ranked #1 for about 15 years in a row. And what they did is they implanted silicone rubber over here, and then sibs over here, and they noticed with silicone rubber, which is a standard material in the industry, you got a lot of blood vessels that grew to the disc because it was nourishing the capsule around the disc. And there were lots of myofibroblasts which generate scar. Whereas with sibs, they didn't see any of this. No neovascularization, no myofibroblasts. So we knew we were onto something, we just didn't know what. So I met with Jean-Marie Perel from Bascom Palmer and the late Francisco Fantes, and put her feet up on a desk and said, well, where can we use this? And I guess it was Francisco, who was a glaucoma specialist, says that if you can make a tube that can drain fluid from inside the eye to somewhere else and drop the pressure without having a plate, this is the holy grail of glaucoma. So we said, okay, let's do that. So some people in here I notice know what the eye looks like, but just for those of you who don't, this is the cornea, the iris, the lens, the retina. And I've learned this from the ophthalmologist, that if you're going to work in the anterior segment, you really don't care about the rest, so you may as well erase the rest of the eye. Okay, and then you can color it in if you have nothing better to do, which I like to do. So here you have cornea, iris, lens, and because it's symmetrical, we can get rid of half of it. And now we're going to rotate it. And it looks like this. So keep in mind, we have cornea, iris, lens. So let's talk now about the fluid that fills the eye and drainage in the eye. So the ciliary body here produces the aqueous humor, and it travels, yeah, here it is. It's traveling below the iris, above the lens. It fills the anterior chamber. And if everything goes right, it goes through this trabecular meshwork into a canal called Schlemm's canal. Then it goes through collectors, actually. And from the collectors, it goes into the veins of the sclera. And eventually it goes to the episcleral veins and out the eye. So this is what happens in the normal eye. But in the not so normal eye, if you have a disease, and glaucoma is one of them, these drainage passages could get blocked. So I'm going to represent it by putting a brick wall here. We don't quite know where the blockage is. But all we know is that, I got to hurry up and talk here because I'm running out of time. So glaucoma is an increased pressure in the eye, and if uncontrolled can impinge on the optic nerve and cause permanent damage. So what we do is we take a tube that we make, and the tube's made out of sibs, and we implant it right through that resistance. Come on, Mr. Tube. It's running a little slow here. So now we have a tube that the body doesn't recognize really as being foreign, and we can bypass the entire resistance, and the flap is closed. Okay, so let me move on. So this became the InFocus microshunt. And it's sibs. This is in on my finger. It's soft, it conforms to the eye. The lumen is long to bring it to where we want, and the fins on it over here prevent migration of it. And another thing, because we're a lot of engineers here, you know, I was taught the Hug and Purcell equation, and basically it's your velocity of your fluid is equal to your pressure drop times the square of the diameter divided by the viscosity and length. And you can manipulate this, where flow is VA and area is this. Now, PowerPoint has a tool not many people know about where you can combine equations. So we combine this equation, and out comes that the diameter you need is the fourth root of these variables here. So very sensitive to diameter. We needed about 60 microns. So here's a healthy eye. Here's where you want your pressure between 10 and 15, sorry, between 5 and 15 millimeters of mercury. So these are sick patients who are not controlled on medicine. We've gone on 5 years now, and we can keep them into the zone of no progression of glaucoma. And most of the patients are off of meds. And we can look at the eye with time, and we don't see any encapsulation. Let's go. I get extra credit because this doesn't work. Okay, we can also put 2 devices in there. And so we're shifting it. I only have 1 slide left. So it's a paradigm shift. We have a replacement for trabeculectomy. We have a replacement for some laser procedures, very little post-operative care. Maybe eliminate the need for eye drops for glaucoma patients. And we can reproduce it in many devices in the same eye. So we were successful. We just sold to a Japanese firm for $225 million. We had another lifestyle change down there. We have milestones that may reach 700. So we've had over 1,000 patients implanted. We're approved for sale in Europe. There's a worldwide demand. It's very exciting now providing all this. And you can read that. This is my shower in my room. We're running out of space. We have to expand. So pursue the product enabled by the biomaterial. Don't pursue the biomaterial. Select the product that serves the largest number of customers. Nylon 12 made angioplasty a reality, helped establish the fields of interventional cardiology, radiology, neurology, and oncology. Over 100 million patients treated, financial impact greater than 100 billion. Cibus biomaterial became the largest selling drug-eluting stent. We're changing the treatment paradigm for glaucoma. And what's interesting, and I'll end it on this, is just a small group of entrepreneurs in West Kendall here, 20 minutes west of here. We can compete very successfully with Silicon Valley, Irvine, Minnesota. I threw in Rochester for you, Dr. Berg. And Stephen Leacock, and there's a lot of people who have to be thanked for this. Thank you.
Thank you very much, Dr. Pinchuk. We'll now have to save questions for the panel discussion later. Right now, we're going to have a 15-minute coffee break. I would appreciate you returning to the room in 15 minutes. Thank you. Our next speaker is Dr. Matthew Terrell, the director of the Pritzker Institute of Molecular Engineering at the University of Chicago. His talk is entitled Protein Analogous Micelles, Versatile Modular Nanoparticles on Control for Diseases Without Symptoms. Please give a University of Miami Cane welcome to Dr. Terrell.
Thank you very much. I'm extremely happy to be here. I've never visited the University of Miami before. There are some contrasts between the University of Miami and the University of Chicago. One is that in 1939, after having won the first Heisman Trophy in college football, the University of Chicago dropped football entirely. I guess we needed to quit on the slim chance that we were ahead. We haven't been engaging in football for a couple of decades. And the other thing that the University of Chicago hadn't started to engage in until 2011 was engineering. It had a, self-image of purity and rigor. But thanks to our current president, Bob Zimmer, who is a pure mathematician but has been at the University of Chicago for about 40 years since he was an assistant professor, we've brought in engineering. So I want to tell you, before I tell you about the title of my talk, which I'm going to aim, because of some of what's gone on already today, toward cardiovascular disease as the target. I want to tell you a little bit about the Institute for Molecular Engineering at the University of Chicago. Why, after 120 years, did a university that had this kind of self-image start engineering? And one of the most important reasons has already come up. We wanted to move the university from the Bohr's quadrant of pure research into Pasteur's quadrant, where you have the interplay between applied science and basic science. And it wasn't any kind of abandonment of pure science. In fact, Bob Zimmer often says that what's really going on is that applied problems stimulate new basic science. And so that's one of the things we're trying to bring to the University of Chicago. Another more local and practical reason is that since the Manhattan Project, the University of Chicago has managed Argonne National Laboratory for the Department of Energy, but yet hasn't had as deep a relationship as it might have. And with engineering, we're really trying to change that. And then just generally, in the spirit of what we're talking about today, we want to instigate activities that are going to bring more products of the University of Chicago into the world. So if you're going to start engineering after 120 years of existence, and there's already dozens and dozens of great engineering schools, how do you even justify that you're going to do that in the overall world of engineering? And that's a thing that we've grappled with a lot. We want to do it a bit differently. Rather than building a school based on traditional disciplines and providing deep and kind of secular dives into individual disciplines, we are aiming to create a more integrated engineering program where we are bringing in bioengineers, chemical engineers, electrical engineers, but also biologists, physicists, and chemists. And our attitude is that the discipline is engineering. Very few really broad engineering problems are solved by people with one particular engineering discipline. So we want to do what we can in various important fields of engineering to translate science into technology. So we have built our faculty based on themes, not departments. I came with the authority to hire 25 faculty members. We've hired 21 so far in the first 6.5 years, and our mandate has been recently increased to 35, so we're still actively hiring. And these are new additions to the University of Chicago. I won't get into a lot of the details, but we call ourselves an institute, but we are a fully autonomous academic unit. That is, the faculty are hired in our institute. We have a PhD program, we have a bachelor's degree program, tenure is in our department, and so on. So we're kind of a combination of a traditional academic unit and a research institute. And we're trying to focus on big problems and training our students how to tackle them, rather than reproducing a traditional engineering school, of which there are already many good ones. The themes that have emerged fit our paradigm of molecular engineering, but we didn't choose the themes in advance. By molecular engineering, we don't just mean engineering molecules, we mean engineering systems from the molecular level up. A lot like the definition of nanotechnology. We like to stick to our proprietary brand name, but if you wanted to think this is an institute of nanotechnology, you wouldn't be too far wrong. And the themes, as I said, weren't picked by me in advance, but rather had to do with people across a broad spectrum that we were able to attract in soft matter and polymers, in materials for quantum information, in immunobioengineering, molecular engineering for water technologies and energy storage and harvesting. I could tell you how we got into each of these, but each one we feel has problems that rise to an important level of significance for society, and perhaps more importantly, in a place that's proud and wants to be competitive. If we focus on certain areas, then we think that we can be competitive at the very highest level. Dr. Moten and I share a Berkeley heritage, him much longer than me, but Berkeley's motto is comprehensive excellence, meaning they're good at everything they do. Maybe they're good at everything, I should say. We're narrowing that to, we want to be good at everything we do, but it's a rather heterogeneous coverage. And we are starting to see synergies, for example, between quantum information and bioengineering, in that quantum signals emanating from the solid state can be very sensitive sensors and so on. But I want to focus for today in explaining what's going on immunobioengineering. I was chair of bioengineering at Berkeley for a couple of years. Every good bioengineering department has programs in drug delivery and in tissue engineering and regenerative medicine with good reason. These are great problems, but they're covered. You know, the great bioengineering departments have a start there that's, you know, decades ahead of us. We want to focus on something that isn't as well covered, and with the people that we were able to attract, Jeff Hubble and Melody Swartz, we have some of the leaders in thinking about what engineers can do in immunology and the immune system. So that's a way of thinking about our philosophy. Like you, we have a new building. Like you, we've invested in a 10,000 square foot clean room that's been very important to fueling our efforts and is affecting all of these different interdisciplinary areas. So it sounds to me from what I've heard that you're very much on a strong track here in going along your own directions in technobiology. And doesn't show up too well, but this is what our faculty looks like, literally. These are the 21 people that we've attracted from various places around the world to the University of Chicago. I've tried to cluster them around soft matter, immunoengineering, water resources, and so on. But just to give you an idea that there's real people there, and we're on our way to trying to create something hopefully special and powerful in the field of engineering, research, and education. Okay, I'm switching gears entirely now to what I do and what we started to do about 10 years ago in creating self-assembled nanoparticles for various kinds of bioengineering applications. And we've looked at nanoparticles for cancer. We've looked at nanoparticles for immune stimulation. We've looked at nanoparticles for intervening in protein-protein interactions. But I decided, partly because of Dr. Pinchuk's talk and partly because it has been our main focus over the last 10 years, to talk about nanoparticles focused on heart disease. And this is the way that we make these self-assembled nanoparticles in our lab. The basic particle that we make is a self-assembled object, meaning it's brought together by association of a tail group, which is usually hydrophobic. I'm going to talk about some electrostatic micelles later on in the talk, with a peptide head group that conveys some kind of biological activity, and often a bigger hydrophilic spacer than you see here. These are synthesized in our lab with a precise molecular structure, and to make things simple to think about, molecules such as this typically associate into very well-defined size structures. If they're spherical, like this, which is what I'm going to be aiming at today, they have about 100 molecules in them. But the beauty of self-assembly is they don't actually all have to be the same molecule. Molecules with a general structure such as this, if you have the same tail group and the same spacer, you can put different peptides into the same object. So you can make a self-assembled object that has different functionality in the peptide head groups. As you'll see, we're going to be talking about functionality for targeting, functionality for diagnostics and imaging, and functionality for therapy. So in other cases, in particular in immunomodulation, which I'm not going to talk about today, it's perfectly okay to have extended worm-like micelles because we inject those transdermally, not intravascularly, and the size of these things doesn't really matter too much. But focus your attention on this, but in any case that we do, having modularity and being able to put more than one peptide into the same self-assembled object is a big help. Oops. Why do we focus on heart disease? Well, in the United States, it's still the biggest cause of morbidity and mortality. About 500,000 people in the United States die of either heart disease or cancer. It's actually been coming down a lot more rapidly in heart disease than it has been in cancer, probably because there's maybe more of an awareness of the lifestyle elements involved in heart disease, but it's still a major killer. And worldwide, cardiovascular disease, especially if you combine ischemic heart disease with stroke, is so big that cancer doesn't even get into the top 10. So, you know, I'm not saying that people in nanomedicine shouldn't work on cancer, but I'm saying more of us should work on heart disease. That's really my only point. And this doesn't show up terribly well, but this is a review article from 2014 about nanomedicine approaches to cardiovascular disease. There's about 30 papers cited there. The one in yellow is one of our first papers from about 8 or 9 years ago. If you tried to make a list of nanomedicine applied to cancer, you know, the whole scroll would probably fill up this room. And, you know, that's, again, it's worthy. I'm not saying people shouldn't do that. I'm saying there's an opportunity here. We could talk sometime later, maybe in the discussion, about why there's so much disproportionate research on cancer. It probably has to do with psychological and other kinds of factors. This is what atherosclerosis looks like in a more detailed way. And you shouldn't think about this as a snapshot in time. You should think of these as slices in time as the disease evolves. And it starts with inflammation caused by lipids penetrating the blood vessel lining. And then the next thing that happens is that white blood cells, monocytes, are indicated that something's wrong by upregulation of receptors on the blood vessel lining. They penetrate the blood vessel lining, turn into macrophages with the aim of trying to transport the lipid out, but they don't always succeed. And over time, and this is a very slowly developing disease in most cases, you build up an atheroma that consists of dead cells and lipids. And as I said, this can take many years to develop, but in the late stage, you have something like this. And this is really where what I'm going to talk about diverges a bit from what Dr. Pinchuk talked about. There are sort of two end stages here. One is that the fibrous capsule covering the atheroma is robust. It's physically tough. And the atheroma can continue to grow until you get symptoms, and typically chest pain. And at that point, you can have an angioplasty or bypass surgery, and you're good for a couple of decades more. So actually, you know, that's the better outcome of what might happen. The more problematic outcome is when the plaque is what's called unstable or vulnerable, and without any symptoms, it ruptures, and then the blood clot occludes the coronary artery, and that can lead to a very severe heart attack or death or a stroke or some other kind of much more severe event. And that's what we're trying to have a nanoparticle that will tell us about. So, you know, I talked about the stages, the initial inflammation, the monocytes coming in, then a later stage, and then finally fibrous capsule rupture. About 7 or 8 years ago, we started looking at a micelle made in the way that I described, except the one big chemical difference is we have a 2,000 molecular weight polyethylene oxide spacer in between the peptide and the hydrophobic group that drives the self-assembly. That's to make sure we get spherical nanoparticles. These polyethylene oxides drive this thing into a spherical structure. And we put on here a short peptide that we discovered with a Santa Barbara colleague at the time, Erkki Rusladi, with in vivo phage display. He found this by putting phage into mice models of atherosclerosis, that this 5 amino acid, cysteine, arginine, glutamate, lysine, alanine, not all amino acids have a pronounceable sequence, but this one does, so we call it CRECA. And CRECA binds avidly to a specific sequence in fibrin blood clots. And it turns out that plaques that are likely to produce a massive blood clot typically are decorated with microscopic ruptures. So having a particle that homes to blood clots is a way of identifying vulnerable plaques. So it looks like this. We put a fluorescent label on it so we can figure out where it went. And again, this doesn't show up too well, but probably well enough. First of all, mice don't get atherosclerosis. They die of old age after 2 years, and this disease takes a long time, and they generally eat healthy during those 2 years. The way you get a mouse model of atherosclerosis is you buy from Jackson Labs in Bar Harbor, Maine, a thing called an ApoE knockout mouse. These are mice that genetically do not make a high-density lipoprotein, what we sometimes call good cholesterol. And then these mice, fed what's called a Western diet, get atherosclerosis in 10 weeks. So this is, and they often become obese. This is an example of an ApoE knockout mouse next to a wild-type mouse. You probably really can't see this, but the lumen of blood vessels around the heart in the wild-type mouse is perfectly clear, whereas there are major atherosclerotic plaques after this mouse has been conditioned for 12 weeks or so. And the first kinds of experiments, thank you, still doesn't work great, but it'll help with this one. The first kinds of experiments we did were to condition the mice, inject a suspension of our micelles into the tail vein, and then sacrifice the animals after 3 hours. And the result is, if we have a fluorescently labeled, peptide amphiphile micelle, but no peptide, just the fluorescent label, and that's the kind of micelle we inject. We have no targeting, and when we excise a blood vessel from around the heart, and we're actually looking at the aortic branch here, we see nothing. But if we target it with the Craca and the fluorescence, we see green fluorescence in the aortic branch, indicating that our micelles are binding to atherosclerotic lesions there. These are some controls that I won't get into. So this was first published 8 or 9 years ago and showed that we could target vulnerable plaque in these mice. We could also actually see where these micelles went, and they tend to go very disproportionately to the region where the covering, the fibrous capsule over the atherosclerotic plaque separates from the blood vessel wall. That's where the macrophages are, that's where the fibrinogen is, and that was our first paper on this topic. I'm trying to keep track of the time up here myself too. So that's great. We can detect plaques that are about to rupture. But actually, we'd rather move back here into this and start to detect the earlier stage development of this disease. And as I mentioned to you, one of the first early stage events is that monocytes are attracted to upregulated receptors on the surface of the endothelial lining, and they penetrate the blood vessel lining and turn into macrophages trying to get rid of the lipid that caused the inflammation in the first place. And a postdoc of mine, who's now a faculty member at USC in bioengineering, did decide when she was in my lab to try to target this monocyte attachment with another peptide that actually binds to receptors on the surface of white blood cells. It's a bigger peptide. The rest of the construct is the same. And the experiment is roughly the same. In this case, she did the same kind of experiment, basically. Conditioned the mice for, in the early stage, something like 10 weeks, in the later stage, something like 12 weeks, and then injected these peptide amphiphiles and looked at where the fluorescence was found in the aortic arch, and she's using a different color fluorescence. We started using green fluorescence, but this is red fluorescence. And you can see that one sees this even in pretty early stage conditioning, and a lot more in later stage conditioning. Again, controls. In this case, what we've injected are peptide amphiphile micelles that have exactly the same amino acid composition, but the sequence of the amino acid is rearranged, so they don't have the specificity of binding in this case. And then, if we can go after that, a graduate student in my lab decided that it would be useful to try to target the upregulation of the VCAM molecules in the first place. So these now are peptide amphiphile micelles that can target inflammation in the blood vessel lining. And this sequence here, or this particular sequence, is one that binds to VCAM. It's taken from a protein known to bind to VCAM, but we just use those 8 or so amino acids. With mice, it's not necessary to sacrifice the animal to see fluorescence, so in our more recent experiments, we've been looking at fluorescence from anesthetized living mice. And what you see is if we do not target it, you typically see that the fluorescence ends up in the liver or in the bladder, and we know that these things are generally sequestered in the liver and excreted eventually through urine. But for the targeted ones, the micelles are localized in the heart. We can't see exactly what blood vessels they're in, but without sacrificing the animal, we can still see that these things accumulate in the heart rather than in other organs. So we feel that we have multiple approaches to look at vulnerable plaque and earlier stage possibilities for developing vulnerable plaque. Sorry, I didn't show you the exact data, but we've quantified how much that is with those VCAM targeting molecules. You can't look at fluorescence inside a living human, however. We're too thick. Therefore, the modularity of these self-assembled nanoparticles starts to come into play. And what we can do in the same construct with the same tails is incorporate an image contrast agent. I don't think Jeff Dirk is still here, but gadolinium is something that one can incorporate to enable MRI. And you can see this is in a mouse. We can also see this brightness coming from gadolinium contrast in MRI in the coronary blood vessels of a mouse. So we think we have an answer if gadolinium is a safe enough thing to use. But maybe we could use other things that would have this contrast that could work for enhancing imaging in humans as well. And then finally, what are we going to do about it? And the jury's really out on this, but one thing that we've tried very recently is to deliver microRNAs as therapeutic agents, and in particular, to look at an inhibition of a microRNA that contributes to the pro-inflammatory phenotype, that is, do something that tries to dial back the inflammation that really contributes to this disease. And what we're doing now, instead of making these micelles with hydrophobic tails, we're making them with electrostatic tails. So we make a micelle that has a targeting peptide, and we're going to use the VCAM targeting peptide because that's an indication of inflammation, a PEG spacer, but now a polylysine, a polycationic tail instead of a hydrophobic tail. And the reason for that is that it can bind nucleic acids, which are the inhibitors for these microRNAs. So now we have a micelle that's held together by electrostatic forces, but in the inside is an inhibitor, which is an oligonucleotide sold by Dharmacon, which is designed, or at least discovered, to inhibit this pro-inflammatory microRNA. So these also make well-defined spherical micelles. And we do the same kind of experiment. We condition mice and inject these things into the tail vein of mice. And what I'm comparing here is the size of the lesions that we measure after 16 weeks. And this is when, instead of injecting anything therapeutic, we inject just phosphate buffered saline. This is when we inject the naked inhibitor, so we aren't using a self-assembled object. We're just using this Dharmacon oligonucleotide with no vehicle and no protection. This is when we use a control that is a different sequence, but the same set of amino acids, and this is what happens when we put it in the construct that we've made, where we deliver the inhibitor in the inside of a spherical micelle. And what you see is that the naked inhibitor actually does a pretty good job. There's something to this anti-inflammatory action of these microRNA inhibitors, but ours does a better job in slowing the rate of progression of growth of these atherosclerotic plaques. So we think we have elements of the whole package, and we're in a position, as many people have been for cancer, to cure atherosclerosis in mice that we've given atherosclerosis to artificially. What we really need to do is move this into larger animals to be in a position to try to move it toward human clinical trials. Oh, sorry, this is one more piece of data that just shows this isn't happening by reducing blood lipids. None of these things reduce the cholesterol or triglyceride level. We believe it's acting on the inflammatory response responsible for atherosclerosis. So that's pretty much what I wanted to say. We believe that these self-assembled nanoparticles are very useful as potential therapeutic agents. They're sort of the smallest, most potent and stable nanoparticles. We've found lots of different uses for them. I've just talked about heart disease, but in fact we have worked on certain kinds of cancer therapies and on immunomodulation. And in fact, we believe that this kind of object is actually a kind of a model of protein interactions, in that proteins fold by putting their hydrophobic stuff in the middle and their biologically active, more hydrophilic stuff on the outside. So in some sense, we think that these things bear some resemblance to engineered, but totally chemically synthetic protein molecules. I've gone through this very fast. That's what our group looks like. Several members of the group, Unji went to USC, Blair Bretman is at Georgia Tech, Lorraine Leon is at the University of Central Florida, and these are some of the key players in this. Thank you very much for your attention.
Thank you, Dr. Terrell. I think we have time for 1 or 2 questions, because you did help us out. Any questions from the audience at this time? We'll have time during the panel, but if you have a... Good.
Do these nanoparticles also in response to increased share at the site of the plaque? Load and drugs. Have you looked into shear-induced delivery of the payload?
No, we really haven't, not shear. But we believe there's other kinds of drugs that could either be put into micelles that have hydrophobic cores or hydrophilic cores.
Why don't you continue on up?
Thanks.
Thank you very much, Professor Terrell.
Thank you.
Our next speaker is Dr. Ashutosh Agarwal. He is in the Biomedical Engineering Department at the College of Engineering, but he's also associated with the McDonald Foundation Biomedical Nanotechnology Institute at the university. That's Bionium. His talk is entitled Organ-on-a-Chip Platforms for Drug Discovery and Disease Modeling. Please welcome Dr. Agarwal.
Thank you. Okay, so I have the very unfair job of following Matt Terrell and Lenny Pinchuk, but I'll do my best. Thank you for the invitation and trust and confidence, Dean Tien and Dr. Berg. Before getting into the science, I do want to have 2 very quick advertisement slides for the new clean room. that I helped co-manage. I didn't know we were going to talk about the clean room so much today, so I'm very glad. This is about a year ago, we commissioned Class 1000 and Class 100 clean rooms at the medical school in University of Miami. So we're very proud of state-of-the-art equipment, both E-beam lithography and photolithography, as I said, in Class 1000 and Class 100 rooms. They are housed in the new Converge Miami buildings, which you can see, the all-glass building from the highway, from the I-95. And in addition to all of this latest equipment, we do have staff, which is very willing and competent to work with you on your design needs. So even if you didn't know the intricacies of how you would go about fabricating something at the nanoscale, you can come and talk to them and brainstorm with them, and they will help you with that process. So look us up, and we're open for business, both from academic partners and non-academic partners. All right, so my talk's about organs on chips, and this is something I got into during my postdoc years at Harvard. So I submit to you that the process of drug discovery is essentially broken. It takes close to today $2 billion and 15 years to bring a new drug target to market. And if you looked at the number of drugs that are approved over years, shown in black dots here, and the cost of discovering those drugs shown in the red curve here, or if you would take that same data and plot it on the y-axis as the number of drugs that $1 billion investment would give you over time. And so the y-axis is on the log scale here. So in about 1950 or so, you could get about 80 or so drugs for $1 billion investment. And in 2000, you could get only one drug for $1 billion investment. This is in complete contrast to the Moore's law of increasing productivity in electronic R&D. So perhaps in a tongue-in-cheek manner, in drug discovery, this law is called the Irum's law, the opposite of Moore's law. So it's very striking. We have a real problem. And if you take a look, and these are real dollars adjusted to inflation. So if you take a look at how drugs are developed, this is the typical chevron chart of drug identification, validation, testing, and submission of your IND packet to the FDA to get clearance for running phase 1 and 2 and 3 clinical trials. All of the testing before the clinic happens in two kinds of systems. Very simplistic, non-stimulatory, very stiff plastic microenvironments, or in animal testing. So let me just try and get the slides to move on. If the person there could just hit a click, you'd get, yeah, there you go. Thank you. So in these very simplistic cell culture dishes, you could test literally millions of compounds in what's called high throughput screening. The argument is the cells are living on such foreign microenvironments that the cells will not give you responses as they would inside a living organism. From those millions of compounds, you could move on. Could you click again, please? You could move on to animal models and test thousands of compounds. The argument here is you have a full organism, but you don't have a human being. Taking these results, you go to the clinical trials, and you end up failing. And by that time, you've sunk in so much money and time that you would have much rather failed in these early models. So those early models are what we like to call organs on chips, where we can capture human-level complexity, but still on a high-throughput system, which can give you results in a cost and time-effective manner. So some of the work I published during my postdoc years, and I've put up the citations here, was in the heart on a chip. So here you're seeing a movie in real time of cardiac tissue built on top of plastic films. So each of those cantilevers is beating because it has two layers. There's a polymer layer and there's a cardiac tissue layer, which I've engineered on top of it. So think of it like a fruit roll-up, but instead of the fruit, you've got meat. And the tissue beats. And when the tissue beats, each of these tabs beat towards you, and you can literally watch and record the amount of deformation produced and convert that into stresses. You can record diastolic stress and systolic stress at the tissue level. And then the difference between the diastolic and the systolic stress would give you the twitch stress. And if one were to then flow drugs, you can get drug dose response curves for known compounds and also, more importantly, for unknown compounds. Could you click on this bottom left image? We also worked on in placing these hearts on chips in very precisely controlled microfluidic housing. So a microfluidic housing essentially is a house with plumbing, And the house contains the heart on a chip, and the plumbing is used to bring the fluids in a very controlled fashion, so you can do wash-in, wash-out experiments of increasing dosages of drugs, for example. Next slide, please. So the very last project I finished up at Harvard was in a human relevant system. We collaborated with a cardiologist at Children's Hospital in Boston who gave us access to patients who had a very rare genetic disorder called Barth syndrome. We had exactly one patient walk into Children's Hospital in Boston. And then by the time the study was going on, we had another patient identified at Johns Hopkins in Baltimore. From both those patients, we got skin cells. So it's very easy to get a skin biopsy. And we converted those skin cells into embryo-like cells of that patient. And then from those embryo-like cells, we differentiated them into cardiac myocytes. Because we didn't do anything with the genetics of that cell, because the cells we end up differentiating also carried the same genetic disorder. And then we put those cells on my heart on a chip. Next slide, please. And these are some of the movies, representative movies from the paper, which was published in Nature Medicine right before I left. So this is about 3 years of work in one slide. Here you have cells from a healthy person converted into cardiac cells, put on my heart on a chip, and you see healthy beating. This is a movie which is looping on the same time scale, and you see almost no deformation. These are cells that came from that patient. These are the same cells. When we introduce the missing gene back into those patients, we can see some of the contraction restored. Now, we can't go in and knock in genes in a living human being, but what we can do is discover mechanisms of disease action. So here we take the same cells, and again, this is a movie that should be looping. I apologize. I wish I had controls here. And could you click on the bottom left movie, please? And so you see some of the motion being restored due to just adding reactive oxygen scavengers or adding linoleic acid. The point is, this gave us a window into how diseases develop, and this gave us a window into some therapeutic options. And I submit to you, this is the future for drug delivery and drug discovery today. On a truly personalized basis, if you could combine the stem cell technology, so they take that patient's cells, and the organ-on-chip technology, you can start testing the effects of known and unknown drugs on a patient-by-patient basis. So with that, I started here, and I laid the foundation. I laid the roadmap of what my lab might do. So I was, obviously, as a young assistant professor, I was I was perhaps a bit too optimistic. So I said I would design 10 different organs, and I would hook them all together. Because the real power of organs on chips is realized when you link one organ with the second organ with the third organ. Because that's how drugs work. Drugs often get metabolized by the liver, and then they hit the other organs and cause toxicity to those organs. And with that in mind, the challenges then are, in the lab, in our in vitro system, we figured out how to keep cell A, cell B, cell C happy by having media A, media B, media C. But that's not how it happens in the body. You've got a universal blood running through and perfusing all organ systems. And so the big problem when you're trying to hook up organs is, do you have a universal media to keep different organ types happy? And more organs also means more engineering challenges to keep these valves and pumps and switches working, bubble-free, sterility, maintain sterility over long periods of time. So this was a big mechanical engineering challenge, purely from devices. And also in the body, there is some scaling that nature has discovered to scale a kilogram of brain with a kilogram of the heart with half a milligram of something else. And we don't yet know what those laws are. We don't know how different organs scale with respect to each other. Is it mass? Is it volume? Is it surface area? Is it the volume flow rate of the blood? Is it metabolism? And so if we don't yet know how those organs are linked, if I design my in vitro organs, I wouldn't know how to make those sizes work out in between organs. And the last challenge I thought of was, even if I do get a response from my micro-human, how do I scale that response back to what a response would be from a complete human being? How do I draw the extrapolation of my results from my dish to the results of a human being? So, this is a long roadmap, and we're trying to pick up some battles and not pick up the other ones. So over here, what we've done in my lab at Miami over the last 3.5 years is build a heart on a chip which captures not just strength of contraction, but electrophysiology. It turns out that the drugs that cause cardiac toxicity, they manifest themselves as electrophysiological in nature. They cause arrhythmias, unforeseen arrhythmias. And so what we've done is, using the same clean room facilities, created, it doesn't project very well, an array of electrodes. And these electrodes can record voltages that are put out by your heart. So this is like kind of collecting like an EKG signal from the heart on a chip. And right on top of these electrodes, we've cultured cardiac cells running in one direction. So we can do things like, so I'll walk you through and this graph. On the black axis on the left, we're plotting the increase in the QT interval of those cells. PQRST curves are what's recorded on your EKG. A normal PQRST wave, normal QT interval is about 330 milliseconds. You don't want those waves bumping into each other, so you don't want any elongation of those waves. Any increase in the elongation is a hallmark of pro-arrhythmogenic events. On the red axis on the right, I'm plotting the decline in the forces produced by the same muscle in response to a drug which is commonly administered in the clinic as a chemotherapeutic and is known to cause heart failure. So we're getting two very different cardiac outputs, strength of contraction and electrophysiology, at the same time in response to the same drug. This work is currently funded by the Coulter Foundation over here at med school as well, which has been very kind to my lab. The second main project I'm switching now to is pancreatic islets on a chip. So this is something I had no experience in. I developed it here in collaboration with the director of the Diabetes Research Institute, which is one of the centers of excellence here. The claim to fame of DRI, this is Dr. Camillo Ricordi, is evaluating different sites for transplanting pancreatic islets that have come out of human donors, cadavers, and then put them back in the bodies of type 1 diabetic patients so that they can start producing insulin when they eat lunch. And this work was recently reported in New England Journal of Medicine. It's a very exciting work. And NIH is taking a close look at this work. And they came out with a challenge 3 years ago and said, these pancreatic islets are coming out of human cadavers, but then the shelf life of these islets is so small, so short, that you have to line up a recipient very soon after you get a donor. And can you do some things to improve the shelf life of these islets? So prolong it from a few hours to a few days or a few weeks. And can you rapidly evaluate these islets before putting them back into a human patient? So with those two challenges in mind, we went in with a microfluidic device that allows perfusion of different glucose stimulations. You can have low glucose and high glucose and low glucose, and bioengineer as well, who would create immunoprotective coatings. The third collaboration we built was with a computational biophysicist who could predict the islet insulin response islet immune response in stimulation to different glucose concentrations. So we had the physics and the time scales already in the computer. And with those time scales in mind, we then designed microfluidic devices. So I won't go in the math here. I'm actually going to skip this slide. The devices today we evaluated a bunch of designs, and this is the power of doing things in the computer. You don't actually have to fabricate anything, spend time and money, but you just rapidly iterate through different designs on the computer. Using first principle physics, we could predict changes like a chamfer at the entrance. So your islets are sitting here, the glucose comes in, it gets directed by this chamfer cut at the entrance, perfuses this islet, and then the secreted insulin gets collected at the outlet. Different geometrical features help guide the flow of both the glucose and the outflow of the insulin. And with those designs, we then went on to do in-house fabrication of these chips. As with every engineering project, we've gone through various iterations of the chips. I'm happy to talk about them if you want to talk to me after the seminar. But this technology of controlling the geometry of the chips to control fluid flow is right now has been patented and is being hopefully licensed by a company in the Netherlands. We can manufacture everything in-house because we have a full suite of rapid prototyping techniques in-house. We have a CO2 laser engraver, a CNC micromilling machine, and a quite nice 3D printer. So we do all of the fab in-house. And again, this is how the chips look. The chips sit inside a clamp. It's kind of like a panini press. So you close the clamp, and it brings the two chips together and creates a fluidic seal. And again, the design features I'm happy to talk about after the seminar. Does it work? So we tested it with rat islets first, and this is the typical experiment with islets is You have them bathe in low glucose for a long period of time, and you record how much insulin they're secreting. And then you quickly switch to high glucose during this region. And then you see if the insulin goes up and then maintains a plateau phase. So this is hopefully all of the healthy pancreas. This is what they're doing. And then you switch it back to low glucose, and the secreted insulin should go down. So it works we tested with rats and mice, and also with human islets. And with human islets, we could see a decline in the health of the same islets over time from day 1 to day 3 to day 8. And this is the challenge NIH. This is what we're trying to solve right now through that grant. Because we are an engineering lab, we're also building a whole suite of fluid controllers and collection stages so that the outflow coming from the chip can be automatically collected in different systems. All this is hopefully also building towards a startup company. We published these results. We were on the cover of Lab on a Chip in March of last year. Okay, moving on. The other engineering complexity we're building into the chip is localized oxygen delivery in situ debubbling agents and in situ oxygen measurements. Again, the details of which I'll leave it to the discussion after the seminar. We're also building within the chip, funded through a second grant from NIH, ways of measuring insulin in real time. So right now, insulin is measured with what's called an ELISA. It's after the fact, it takes too long, and it's very expensive. So what we want to be able to do is see the insulin response of islets in real time through fluorescence techniques. And this is, again, in a collaboration with a PI at the medical school. And this is the loop we try to close with all of the projects. Using the in-house capabilities to do things in the computer first, do rapid prototyping in the lab, and then rapidly test those devices and then go back. And once we are happy with the design, we look for commercial partners who can hopefully make not just tens and hundreds of these devices, but thousands of these devices and distribute it. And that's exactly what's happening. The grant is through a consortium, and we supply the chips to the other partners of the consortium in San Diego, at Harvard, in Israel, and in Boston. The very last piece of data I want to show on the pancreas on the chip is now doing the same things that we did with the heart. From the same patient, we get induced pluripotent stem cells, and we make those stem cells differentiate into immune cells. We pre-activate them, and we make those stem cells differentiate into pancreatic cells. And we want to see if these immune cells attack those pancreatic cells, because that's exactly what happens in a type 1 diabetes attack. So if you could play the movie on the bottom right. Could you click on the movie on the bottom right, please? So here you're seeing a beta cell cluster or a pancreatic islet cluster from one patient, and the immune cells from that same patient come in within my chip and attack this islet and completely destroy it within 18 hours. So if you could play it again, please. Thank you. So you would see how this is a nice, well-integrated islet, and over time, this islet's going to get chewed up by these activated immune cells from that very patient who had type 1 diabetes. Now, this opens up doors for us to go after coatings that can prevent those attacks, go after strategies to control the anti-immune drugs that this patient should be on once he or she receives an islet transplantation. The third project, which I'll quickly cover, is in cancer metastasis. And again, this is in collaboration with my, who I'll talk about in my next slide. The problem we're trying to address here is primary cancer does not kill. It is the metastasis of that cancer that's responsible for 90% of the deaths. So it's the metastatic disease, really, that's the lethal part of cancer. And the way a metastasis spreads, let's say if a patient has breast cancer, and that breast cancer over time will seed a few of those cancer cells into the bloodstream. And these cells are very small in number, and they would keep circulating until at some unfortunate time, they find a home in the lung or in the bone or in the brain or what have you. And at those sites, a small fraction of those cells then start creating a secondary tumor. And that's what kills 90% of cancer patients. So Dr. Richard Cote's lab has pioneered, and this is Dr. Cote, who's my med school boss, mentor, and champion, who's sitting right here. He's pioneered a range of highly precise microfilter technologies where we take that blood and we essentially just run it through a filter. This filter has holes which are sized to the size of that cancer cell, so that all of those cancer cells can be captured, in this example, from breast cancer, colorectal cancer, different cancer types, and it works across a broad range of cancers, both solid and non-solid tumors. He's shown the utility of this over the last 10 years, and what we came in, when I started in shared lab spaces with him at med school, was they could never release the cells. They could capture the cells, they could count the cells, but you want to be able to release the cells to be able to play with them. So we created well-published, we applied well-published technologies called PIPAM. It's a specialized polymer that is hydrophilic at room temperature and becomes very hydrophobic at 37 degrees Celsius. So we ran the patient blood at room temp, and then all we did was raise the temperature to 37 Celsius, in which cells are happy anyway. And it turned out these coatings basically release the captured cells, and now we could get patient cells. And we published this also a couple of years ago now. Now we have patient cells. Now we can start doing drug testing specific to that patient. Now we can start discovering what the primary tumor of that patient is doing without cutting into that patient, right? Without doing a biopsy, we can bleed the patient and get a liquid biopsy. So that's what the focus of these very new projects in the lab are. We are trying to get breast and prostate blood from breast and prostate cancer patients, and we're trying to grow in the lab, tissue engineer a bone niche, a bone marrow niche, because we know in biology, in our bodies, these CTCs, circulating tumor cells, will extravasate, will first start talking to your blood vessel cells, and then, extravasate to the bone and start propagating at the bone. So we've designed a bone-on-a-chip device that has the perivascular niche and the bone niche, and hopefully when we flow in these cancer cells, they will first interact with the perivascular cells. These are the cells that line your blood vessels, and then they can get cues from the bone that I'm here, you want to grow, here are the signals that will help you grow in the dish. Does it work? We have some reason to believe that it does work in the first part of the chip. As I said, we are co-culturing them with, not co-culturing them, we're putting them in chambers with these perivascular cells, and in response to putting them in connection with these perivascular cells, they are upregulating certain markers that cancer cells upregulate when they're of the invasive phenotype. In contact with the bone, they're upregulating certain markers. I won't go in the details of these markers, but these markers are linked to the metastatic malignancy of cancer cells. So they are feeling the presence and responding to the presence of both the blood vessel, perivascular cells, and the bone cells. So we're very excited about this development. A few other projects which I won't cover, but which are also budding up in collaborations with medical school PIs, is in a neuromuscular junction. So we are collaborating with a neurologist, Dr. Suparta. Mario has some patients who walk in with a very rare neuromuscular junction disease called CMT, Charcot-Marie Tooth disease. He gets, again, skin cells from those patients, converts them into stem cells, derives neurons of that patient, and we put them in co-culture with the muscle cells of the same patient to see if we can recapitulate the neuromuscular junction disorder of that patient, The second very exciting project, again, is in collaboration with Alessia, who's in the audience right there. She has been very supportive in guiding us to create a glomerular filtration barrier on a chip, which is for the kidney on a chip. And this project is also, again, as I said, very early. And the hope is once we validate the chip, we can get both cells and patient sera from chronic kidney disease patients and build an in vitro model for diabetic nephropathy. In closing, I would say organs on chips is not new. This was new 7 years ago when I started in my postdoc years. So over the last 7 years, many of those same labs, which I know, have formed startup companies. And the idea is, can we make these platforms not what they are today, which is purely arts and crafts, but something that's robust, right? And we can make thousands of them, and we can ship them to you, and you can use them. And there's a bunch of startup companies that have come out in this space. What I have focused on in my lab is to really do an analysis of how costly they are today, how sophisticated they are, and then where they need to be to really be transferable to the end user. So what we want to do is probably compete with the 96 well plate or the multi-well plate, super cheap, everyone can get them, but they're not on the sophistication axis. They're quite low. So they're very scalable. You can make millions of them. They're very cheap, but they're not sophisticated. My organs on chips right now are extremely sophisticated, but they're extremely costly. And I can't make a lot of them. So through conversations with hopefully people like Dr. Pinchuk, I want to get to, through partnerships and startups, a less sophisticated organ on chip, but perhaps which is less costly and more scalable to manufacture. So we are still brainstorming those things. With that, I'll close and acknowledge the funding sources and the amazing team I have. I would just say, because Dr. Terrell's in the audience, this is the work of one of the undergraduates. The creativity of the undergraduates in the lab is amazing. They get excited, they take pictures, and they Photoshop them to make them look great. And he might end up as a PhD student at the University of Chicago program. We just chatted about him yesterday. All right, thank you very much.
Thank you very much, Professor Agarwal. We have time for a few questions. Okay. If not, let's proceed to the panel with the presenters. Please come up. And now I have the honor and pleasure to introduce to you the President, Julio Frank, who will give some introductory remarks. Then he will moderate the discussion. President Frank is a member of the National Academy of Medicine. He's a renowned international health expert, having served as Mexico's Minister of Health, as Dean of the Harvard T.H. Chan School of Public Health, and as the 6th President of the University of Miami. Please let us give a warm University of Miami welcome to our President, Dr. Julio Frank.
Before I join the panelists, let me just take a second to make a few introductory remarks, and then we'll start the discussion with our very distinguished panelists. I'm very happy to be here. I'm a proud member of the National Academy of Medicine, so we're representing the other academy here, and I'm really delighted to be able to join to moderate this panel with our three very distinguished speakers today. Just a couple of reflections as I was talking with Dr. Berg and with Jean-Pierre about this joint panel. First of all, I am very enthusiastic about this partnership in technobiology, whereby engineering or technology is applied to critical issues in medicine and biology. And I guess now at the University of Miami, we have in the academic leadership of the university sort of a representation of that, because my field is in medicine, and we've just recruited a provost who's an engineer. And so I guess we complement each other, and we are, in a sense, a personification of a technobiological approach to the university. And this approach is really relevant as we're finalizing our strategic plan for the centennial of the University of Miami. We will turn 100 in 2025. And as we went through the process of producing our strategic plan, we thought it was very important, really at the outset, to spell out a vision for of how we understand the university. I thought Dr. Terrell actually addressed that in reflecting on the evolution of the University of Chicago. The way I think about the university is in terms of a single product. We have one product, although it's an incredibly powerful product. Our product is knowledge. And good universities develop an integrated process around that product. I call that the circle of knowledge. We start with the creation of new knowledge, which is what we do in research. We move on to the recreation of knowledge, which is what we do with education. Good education doesn't transmit existing knowledge. It actually recreates it in the minds of the students. And then, and here's the important statement, that integrated process includes a next phase, which is the translation of knowledge. And here's where I think conceptions diverge. Many think that the role of the university ends with the creation and recreation of knowledge. I belong to a camp of thought, very well represented in US and global universities, that says that no, that's not the end of our mission, that we actually also have as a core part of the mission, not an extension or not a service element, but as a core part of the mission, the translation of knowledge. And there's two types of translation. We can translate knowledge into technologies, and we can also translate knowledge into evidence that then informs decision-making at all levels, at the level of a household, at the level of a practitioner who uses evidence to practice, or at the level of policymakers, ideally making policy on the basis of scientifically derived evidence, which is a form of translation, along with technology, which is what we have been discussing. When knowledge gets translated, then it can be utilized. And we actually are engaged in utilizing knowledge, mostly like most universities that have a comprehensive academic health system, through our delivery of services. We use that knowledge that's been translated, we deliver a service. And when you do all of that, and other forms, but that's the most visible one. And when we do that, we then transform reality so the circle restarts again at a higher level. It's more like a spiral of knowledge. We are again into the challenge of creating new knowledge, recreating it, translating it, and utilizing for its application. This, I think the symposium today illustrates that idea, and in thinking about that statement about the mission of a university, then we need to take knowledge translation as seriously as we take knowledge creation and recreation. It's not an issue of just letting individual researchers undertake that translation. You actually have to support it. There has to be institutional support for that function if you believe, like I do, that that's part of the core mission of a university. And that's exactly what we're doing. We sort of express this by, in our case, we've articulated a number of aspirations for our centennial, and two of them, which are the most relevant for today, there's four, but the two of them is that we aspire to be the excellent university, but also the relevant university. And that's the idea that, contrary to a conception that there is some trade-off between excellence and relevance, they actually, I think as it's been expressed here, and it's captured by the idea of the Pasteur quadrant, actually excellence and relevance feed on each other. And excellence means, of course, the adherence to the strictest standards of rigor in scientific research, and relevance means the ability to undertake that translation in order to address the most pressing problems facing a society. Those two values actually are reinforce each other. So I wanted to start with this series of comments because I think for us at the University of Miami, it's an honor to host this joint symposium between the two academies, medicine and engineering, but it also resonates very much with the way we conceptualize the role of the university and the way we're trying to actually realize that vision in the way we organize our work here as we move towards our centennial. So let me now join the panelists, and let me suggest that before we start the interaction and the discussion, let me first allow each of our panelists to give some additional reflections that might have maybe things you ran out of time to say, briefly to complement, or more interestingly, if you have some additional thoughts, having listened to your colleagues. So let me start first with Dr. Leonard Pinchuk.
You can hear me, I guess. You can really hear me.
Everyone else don't know.
Let's turn my gain down. You can hear me, I guess. Okay. So there was a lot to read into what you were saying, in that universities do generate a lot of technology, and you have tech transfer people who are involved with it. And then what happens after that? You know, and how long does the university follow it? In other words, if you get it out of the university, is that the end? Okay, so the things that went through my mind, first of all, is in all the projects I've done, I've worked with universities. Our original lab for angioplasty and stents was at the University of Toronto, only because people I knew who were interested were alumni, and they worked there. And then when I began to know the Baskin Palmer people, we moved it over there. So industry does partner, and we financed, and we also provided incentives. I won't talk the number, but I found it very important that if the university was to test something for us, whether it worked or not, that they get a royalty. And in return, if they create or we joint create, we fix the other royalty. So there'll be two levels of royalty, but I wanted to, if it's a win for me, I wanted it to be a win for the university. And this led to a very good cooperation. So the inventors and professors at the university felt that they, you know, they can reap some of the rewards for it. Where I think the university has a tough time is when they bring the technology to a certain point and they talk to industry. They don't realize sometimes that industry doesn't have the capacity to work exactly on what you think they should be working on. I think a very interesting concept is, instead of bringing it to industry, to find teams of people who have the energy and the know-how to bring it to the next level, where industry has a fear of not getting it. In other words, you bring in a competitive tension. Because when you're too low down, the people you interact with really quite often don't have the vision you have. So you have to bring it to a point where you show it works, and you show that they may not get it. And finding these teams, I'm sure they exist, but I think that's a very important part. I'll just mention in a minute or so. I have this issue because I've been very successful as a serial entrepreneur. And then it only occurred to me recently, traveling with some people who were parallel entrepreneurs, that I can only handle it serially. But some people have the resources to do several projects at once, and these are the parallel entrepreneurs, but they're always out of money. So I've attempted to take on more responsibility, and I've looked at projects at the University of Miami only because I've been pulled into them. And there's a fellow there who's very good at that. But sometimes I feel I'm lacking because I can't provide the attention necessary to bring it to fruition, because I'm focused on my duties I have to do now. So keeping a list of technologies, of really good people, of financiers, and then getting these all together to form a little company or an infrastructure, I think would be a great way to move technology out of the university. And that will help attract the strategics. So that's kind of my thoughts.
Thank you. Thank you very much. Dr. Terrell, any additional thoughts?
Yeah. Well, I found your discussion of creation and recreation and translation and expanding the idea of translation not only into technology but into evidence really thought-provoking. But that's just by way of saying I appreciated what you said. You know, coming to a university that didn't have engineering, I've often found myself over the last 7 years explaining the difference between science and engineering. And our president, who's a mathematician and who's really responsible for this activity, often said at the beginning something like, the boundaries between science and engineering have disappeared. And I never quite liked that statement. I think I know what he meant, that there are many of us in technology that work at the forefront of science, and we have to understand the forefront of science, but there's certainly a difference between a scientific mentality about discovery, which is what you're talking about, knowledge creation, and an engineering mentality of invention. So I think that's an important distinction always to make. But then the final thing I'll say, and I won't go on about this, is I always try, especially with younger people, to make clear that in saying those things, we're not labeling people. The same person can have scientific thoughts and engineering thoughts. It's just that the modes of thinking are a bit different when you're trying to understand nature or if you're trying to change the way the world works, which is what engineers do.
Thank you. Thank you very much. And then Dr. Agarwal, any?
I guess the only thing I might add is when we indulge in these kinds of interdisciplinary activities, the one thing we end up also doing, perhaps not by design, but it's a gratuitous thing that happens, is we end up educating the next workforce who are in the labs, right? So I'm graduating my first batch of undergraduates this year. I've only started 3.5 years ago. I haven't graduated any PhD students, but all those undergraduates who worked for 3 years in such an interdisciplinary environment and got mentored by a stem cell biologist, a chemist, a mechanical engineer, are so ready right now to think about big problems. It might be my personal bias. They're all going up for PhD programs, and when I read their statements, they all want to change the world, and they're not bound by one discipline, one label, one tribe. And I feel like that's an effect of having them in a lab, which was truly interdisciplinary and creative and thinking about big problems. Instead of, here's one molecule, not that that's a bad way of running a lab. Here's one molecule, one mechanism, and we'll spend the next 25 years looking at that mechanism.
Very interesting. Great. So I suggest that we sort of interweave in our discussion some questions that from the audience. If you want to raise any question to any or all of the members of the panel, please feel free to do so. But let me just to warm up the discussion and to allow members of the audience to think about questions. Just ask you to reflect, because the three of you have touched about that in different ways about this particular issue, which is the sort of disconnect between what we need in terms of interdisciplinary research and the structures we have created. I mean, again, Dr. Terrell, because you had the opportunity to launch something new, you were able to be deliberate about that at the University of Chicago. And I thought it was fascinating to hear you say how, you deliberately created something that was designed not to be a traditional college or school of engineering, and not to be based on disciplines, but on themes, as you call them. But that's not the reality in most of our research establishment. You have the weight of structures that have been there, and trying to break out from silos to engage first inside the university environment in interdisciplinary work, as Dr. Agarwal was saying, or breaking out of the silo that the university itself represents with respect to the rest of the world, as you were just mentioning, and creating those bridges is a challenge. We tend to be territorial and build a silo. So I wanted to put this out as we think about the frontiers in technobiology and the promise of what would really be much more of a problem-based interdisciplinary approach. How have you thought about this problem and in your own practices, which we have obviously been doing it, what reflections do you have about how do we bridge those silos and then focus more on problems than on disciplines or on institutional settings, like having a university here and entrepreneurs on the other side. How do we better integrate both internally across disciplines, but also as we seek partnerships with the rest of the innovation ecosystem?
Well, I don't know that I have the answers, and our program is still in its infancy and experimental, so we're still playing around with how to do things the way we really want to. But I might point the finger to Ashu here, because I'm quite sure at the Wyss Institute at Harvard, one thing that they've done is made it very easy for industrial people or entrepreneurs with experience to actually be there in the lab, and not just entrepreneurs in residence that sit in an office and somebody comes and talks to them occasionally and they tell war stories about what they did, but people that are involved in the research projects and say, okay, you have some choices here. You could go down this alley and that might be interesting scientifically, but if you pursued this lead, you'd have a lot better shot at it.
That's exactly.
Over to you. So.
They come to group meetings every week, and they sit in on presentations, which are mostly about science, and they do exactly that. They identify the bifurcation points in a research program, and they say, if you go down this path, you'll get a Nature or Science paper, and it'll die. Nothing productive will come out of it. And if you go down this path, you have to think about the translatability or the manufacturability of the system.
I don't know that I'd throw Nature and Science papers under the bus like that, totally, but I hear what you mean. Yeah, so. So that's one thing. Creating intimate contact between people who really have experience in creating technology and people who aspire to create technology is a good mechanism, I think.
Any
thoughts? A comment, because I spent my entire career in industry, not in academia, so we kind of hit the problem a little bit later. But I was I think I'm the first biomedical student in the state of Florida. I know they tell me I'm the first in the University of Miami, but there were no other programs, so I'm probably the first in the state of Florida. And when you go through the biomedical engineering curriculum, it's multidisciplinary. It's a multidiscipline curriculum, and you learn a lot. And I found maybe halfway through my career telling myself, I should have paid more attention in that class. But I've also used just about everything I've ever learned. And then later, when you have a little bit of money, you begin to hire the consultants who are really experts in that. So, I'm visiting with a group at UMiami in statistics, because it's just beyond my it's more than just average and standard deviation. So, I know my limits. Again, working with Baskin Palmer, they have just specialists in different areas that, I never got to know that. So you learn how to reach out. You get the general interdisciplinary knowledge from your curriculum, but you have to know to reach out to people who are really experts in specific areas. And that's what happens later.
Very interesting. Any questions or additions to this discussion from a member of the audience? Please. Hi.
I'm extraordinarily fascinating. To start with, I'm a physician, but in Michigan, I was a research fellow. So I went from, a small muscle cells culture. My expertise is actually in red cell potassium transport. And in the early stage, because that was some years ago, we were even dealing with nanotechnology. So after that period of time, here I am. I'm a physician. So physicians to integrate research is something really extraordinary. And to have people out there, like you guys, services and institutions that can actually communicate and integrate with physicians that are doing research as well. Because at the end of the day, it's the life of someone who is, we're doing research and we know that something will work or not work. But at the end of the day, somebody who's going to die or somebody who is going to survive. I'm absolutely at awe that we can do this here at Miami. I brought my children. They are teenagers, and I want them to understand what it is to be at the University of high caliber. And also, there are not many girls, but girls need to understand that girls do research. And they can be leaders, and they can do clinical and basic research. And there's not, in terms of what you guys are doing, there's not an absolute contraindication between clinical research and biotechnology. It's actually, there is a point where we all can meet and do something for the population in general. But now I need a question for you. When you do your chips, and I would love to be able to meet and talk, my major interest in is protein and the red blood cell proteomics and transport. When you do your chips and you're testing the different organs, I guess, were you able to put blood in there? Can you put blood? Can you study the interaction between red cells and these models that you have in chips?
In the context of a particular disease?
Well, and this is what's fascinating about the human being. I mean, the red cell itself is like an endothelium cell, only that it doesn't have nucleus.
Right.
So interacts with the endothelium the same way the endothelium interacts with any other cell. So for me, in order to test the ability of this chip, right, I have to put what people live with, which is blood. So that's what I'm asking, if there's any way
Right.
technologically.
No, my answer so far is a qualified no, because we do get blood from cancer patients and we get circulating tumor cells out of those, but we throw away the rest. There are a lot of labs I know of who deal with, for example, sickle cell anemia research with red blood cells that are sickle cell level. We are more at the tissue level, so we force many of those cells to form, tissue engineered systems. So our readouts are more at the tissue level. But that doesn't mean you can't.
But you know what I'm trying to say? I mean, the cell needs the tissue, the red cell needs that oxygen that will. But anyway, I have to say congratulations.
Thank you.
This was extraordinary.
Thank you. Any other, please?
My name's Eric. I came down from North Carolina for this event. Over my time, so from each of the speakers, I think it's extraordinary. I've met one of you, and I'm going to meet another of you today, I hope. Two thoughts and then a question. One is clearly the role of the university has to be evolving from basic science knowledge creation to translation, because industry is moving further downstream. That is, they're not investing in research. I came first out of telecom in my first career, with Lost Bell Labs, for example. And so I see this gap kind of increasing between the traditional role of academia and what the universities have been doing in knowledge creation. So I find it just extraordinary to watch and extraordinary to participate in. And I've had a debate with another colleague of mine about the difficulty of translating. A colleague of mine's view is, if it's good, it's a good idea, it first gets to, let's say, Nature and Science. If it's really good, somebody's going to pick it up and it will find its way through. So my real question is, do you believe that, or do you believe that good ideas in the university language because we don't have the right tools to grasp?
Those are the structures you were talking about.
Right. But go ahead and I'll add some.
And I'm sorry if I'm a little bit redundant, but I've been in industry and I've been on committees where you look at technology. And sometimes it's easier to say no, because if you say yes, you have to put a lot of things in action. And then if you say, and if it's a technology that's not ripe yet, it has to go through your R&D department. And they're usually working on other things. If you reach a point where you don't have to do R&D, you can use what's called the M&A money, merger and acquisition money, which is a whole different fund that doesn't show up on your P&L. But if you can use M&A money, it means you're not going to be doing more research. It's ripe for production. You see, if it shows up on your P&L, then your profits are less, and the CEO doesn't get his bonus. right? So it's got to come out of M&A, so you have to be at a point where it's ripe. And that's why I said before, if you can find somebody to bridge between the professor and when it's ripe, and to bring it up to a point where there's very little, you never use the term R if you want to get M&A money, you have to use the term development, D. You have to bring it to that point where there's very little work by industry to move it forward.
Let me then just ask, so the problem then that you're suggesting is there's not, or how other people might define the problem, is there's just not enough capital to move ideas from the lab to that point of M&A. So there's a lot of capital in Silicon Valley, there's a lot of capital involved. So I restated the question. Do you think there's enough capital and just a lack of good ideas, enough capital and a lack of, let's say, partnership to actually execute on ideas, or not enough?
Well, also the problem is finding who has the capital. There's something like $3 trillion that people want to invest, but how do you reach those people? So sometimes you look at people who have accomplished a successful exit, and they usually have investors. If you can find those people, they're willing to go into private placements, to raise the money if it makes sense. It's a little bit more difficult to find. Venture capital early stage is very hard to find. I don't think we had any venture capitalists in any of my companies in the last 10 to 15 years. We relied on angels to some extent, and then industry came in very quickly. So it's difficult. There's no easy solution to that, of how you find that original money. But publishing, being recognized, helps a lot because people begin to know who you are. And it just takes time. I'm sorry, I can't provide a panacea answer for that.
But if you, looking at it from the university perspective, I think in my conception, if we agree with the premise that knowledge translation is a core part of the mission, it's a core dimension of the mission of a university, then you need to create the institutional structures to actually make sure that it happens. And just like, we support, we attract talent, but then we create structures in universities to support the knowledge creation, the research mission, and we support the recreation, the educational part of our mission. And if we don't want our job to be done when you publish, although we do value publishing, right? I mean, that is important. It creates, but we think that we need to take this to the next step. The universities need to develop the structures to make sure that that knowledge translation actually happens. It cannot be, we have sometimes incredibly talented researchers who take it upon themselves and who have the imagination and the creativity to actually go out and develop startups and raise money and be incredibly successful also as entrepreneurs. But that's not the generality. I think the university needs to create those structures. That's what we're trying to do here, and that's what many universities are doing. But we're still faced with there is a camp that will say that that is not our job. Our job ends, our commitment to society ends when we publish the results of our discoveries, and then it's up to other social actors to take that up and translate it. I am saying that we should also be involved you mentioned when do we sort of transfer literally? That is a valid question. What are those frontiers? And that was what I was asking the previous question on not siloing the university itself, but actually have a much more open interface with then partners that can take the next steps. But that has to be part of the institutional makeup. And the question is, are we organized like that? And I think you were sort of suggesting that University of Chicago went through some rethinking.
No, definite, serious rethinking, that's right. But back to what you were saying is, are things languishing? I think some things are, and they are for the lack of some of the things that President Franks is talking about. Even if you don't want to be an entrepreneur, I think university faculty should be increasingly sophisticated about intellectual property, because just publishing something might actually make it impossible for somebody to create technology out of it. And of course we want to publish, but there can be a sequence of things that opens up a lot more possibilities than the simple publication route. And I don't think even myself have been in recent years as sophisticated and as effective along those lines as we might be.
Let me make just one last comment, and I'm probably going to embarrass somebody in the audience here. When I was, I guess, 32, I started my first company, and the chairman of Biomedical was Dr. Peter Tarjan, and he put in a chunk of money, and the dean of engineering put in a chunk of money. And I'll quote what you said. He said, with Pinchuk's brains and Norm Weldon's greed, something's going to come out of this. And it did. And then they put it in again and again. And there's other people in here who I won't mention who put in hundreds of thousands of dollars. And there's one person here who put in over $1 million. So when you do the first and you get the money back, then they'll believe in you. So you got to get people to believe in you. And maybe you can get that seed growing.
And by the way, I would just add for the need to reinforce this need for some sort of symbiosis. As funding for basic research becomes much constrained as it is through a combination of fiscal crises that are about to become even worse, and skepticism in some quarters about the value of science, I think universities actually need to engage in knowledge translation, particularly on the technological front, to identify new sources of funding to keep the basic science engine running. You cannot translate knowledge if you don't create it. So keeping that funding for that machine, which starts with fundamental basic science, which is the whole idea of the Pasteur quadrant, is also another very pragmatic reason to actually engage in this, even if you have an ivory tower sort of conception of the university, just a very pragmatic turn, as the fundamental compact between the federal government and universities that was established after World War II is eroded, and we see an erosion of federal support for basic science. I think we need to be creative in other sources of support. Anyway.
I'm pretty loud. Just Len's done a great job of promoting our environmental engineering here at Bascom Palmer. But just not just plans or anything, but Eric is actually here to give a talk at the Biomedical Engineering School on Wednesday. By visit. He's actually an entrepreneur with a startup that was at Duke. That started out from Duke, spun off with a company, purchased, became the CEO. He's now here to present capital, giving a talk Wednesday, 5 p.m. at the MacArthur on his experiences with medical startup. And this is Len's versus
That's good.
in person versus email connection.
Okay.
Awesome. Can I just add something which would I would segue from your comment about the sophistication of the people and knowing what IP is, knowing who the customer might be, how big that segment is, and how to get there. So it's incumbent on the PIs to be more aware about this. This graduate students need to be more sophisticated about this. The deans need to be more sophisticated in valuing the activity of the professors who are doing these kinds of things rather than, the more mundane academic work. And counting that towards P&T, I think those structures need to change. But having said all that, structures and silos are important. But if someone wants to go out and do it, I will paraphrase Alessia here, who's sort of my mentor here and who's done a lot of this, and Alessia, I'd love to get your input on some of the discussion here, because you really are doing all of these things. If you really want to go out and do it, you go out and do it. You don't get bogged down by who's my chair, who's my dean, what's my school, what's my tagline. And you go out and seek it out.
Just do it.
Yeah.
Please.
I wanted to thank all you gentlemen for the really stimulating talks that you gave. I come from a non-academic background, and it was interesting to me when I hear Dr. Pinchuk speak. You know, basically, when you started your company, it sounds to me like for your first product and many others, you had a basic set of skills. But the key to the success was finding a problem worth solving. And then you went after it. Whereas when I heard the other gentleman speak, I was stimulated from the point of view that you were creating not only knowledge, but you were creating a capability. And all ideas were spinning into my head as to where it could be used and what problems it could be applied to. And if you talk about, you know, what is the missing link between the university and Dr. Pinchuk's venture, it's that fellow that was greedy. It's the greed aspect that has to be added to the formula. And whether you call that venture capital or hungry students that want to go into the business world, but that is the key transition element in my mind.
Yeah, no. You know, it's, I'm trying to get my train of thought back here. It's not as much the greed element, but when you have somebody who's done it before and sees low-hanging fruit, it's there for the taking. So maybe we can call that greed. The question is putting it together. I've always said that engineers have a lot of solutions. We just don't know what the problems are. So you got to find the physician in my field and figure out what has to be done. Now, you know, in the grandiose aspect, we know the use of an artificial pancreas makes a heck of a lot of sense. There's a lot of people, the market is there. It's just a challenge of getting it done. So, you know, this is what you're basically working on, and same with atherosclerosis. But it's good to have. Norm Weldon was my CEO. We left Cordis together. He was CEO of Cordis. So he did the business end, and I did the technical end. And another little thing that was important, although we were co-founders of the company, I was never on the board of directors because he said, Len, no one knows you, so you're not going to be able to raise money. But he made me secretary of the corporation. And he said, you just record the minutes, although he always had the minutes written before the meeting. But I learned a lot from him, and this is why I said in my little talk here that the key to success is to surround yourself with people who are in the know, who know how to do it. Get a board of directors mainly of people who know how to raise money and have the connections to raise money. And if they believe in you, they'll tell other people to invest. And this is how you start.
And I mean, that's why we talk about building an innovation ecosystem. And I think that analogy is well suited. You need different species interacting in that ecosystem. And I think the sort of evolution of thought in universities is that if you look at any successful of those innovation ecosystems, there's always a comprehensive research university, at least one, right at the core. And this is what we're trying to do here in South Florida. I mean, there are a few exceptions, some of your companies, others, but most of them are in other parts. I think building that ecosystem requires to have a comprehensive research university, and then all the other elements, the venture capitalists, the intellectual property experts, the inventors who can take some of those ideas and then actually make them into products that can satisfy a particular need or develop a solution. It's that interaction that I think is what you find uniquely in successful innovation hubs. But I would stress that every one of those has a research university at its core, because the engine that keeps this running is the basic research that then becomes the subject of all the other. And then as startups fail and face difficulties, they feed back into the set of questions that basic research can address. Please.
University of Miami undergraduate, majoring in microbiology and immunology. So again, thank you for your presentation.
very good question from a microbiologist. Well, I'm an engineer. One of the things that I had difficulty with was the fact that you don't kill cells when you use radiation. If you kill cells, you have necrosis. So you do have a disintegration of the tissue. So you really have to stop the reproduction, but keep them happy, but don't let them reproduce. And this is what stopped the restenosis. But you're right. You're right. If you don't have that defense mechanism there, and it is traumatized and something is happening, I don't think it's the proper solution. Fortunately, and the same with the chemo drug, by the way, the drug-eluting stents. You're turning off the repair mechanism to some extent. So I wouldn't say you're as strong and immune as you used to be, but perhaps Dr. Terrell will, maybe you can add something to that.
No, I think I can't. I can't add anything to the radiation part of it, I'm sorry. So.
Yeah, so you're right. And while we're at it, I think my macrophages were a lot cuter than yours.
They were.
Thank you.
I speak very loud, so I think it will be okay. Thanks, everybody, for having us here today. I come from the medical campus. I'm a physician, just like my colleague said. I went actually to round this morning at 5 because I'm the physician on call to be able to make it to this event. Because I really respect this potential interaction between, this campus, the medical campus, engineering and medicine. And I really would like to make sure, I learn a lot when I work with the quad exercise from Professor Pinchuk about really why are we lacking innovation, why, as President Frank just said, why this should be an exception rather than the rule, When we work in the quad with Ray Sanchez from the School of Music, we said we should learn from the School of Music. Everybody is, like, the way you advance is through copyright, no? That's the way you actually build your CV in the School of Music. Why we cannot do it in the medical campus, why we cannot do it in BME, and encourage and train our students, our leadership, to recognize innovation, bring it forward, and really shoot for this example that we are all aware today. They are exceptional examples. If we see what he has done, it's fantastic. We are a unique institution in South Florida. We have no competition. We have 6 million inhabitants. This was an observation that I steal from one of the person interviewing for the Frost School of Chemistry, and we are failing to actually build new companies and be present in the community and work with the community to build stronger companies. And I really would like to have your commenting on that, your take into this. Thank you.
And just to explain to our visitors, you're referring to the quads. The quads were groups of 4 faculty members from different parts of the university that worked on some of the elements or initiatives of the strategic plan, and that's
yes.
that's
and I was part of the quad of innovation
right,
with Professor Pinchuk.
And there was
Thanks.
right. So, any thoughts on?
We don't even have in our template CV the patents and the companies. I'm CSO to start a company, but nobody cares in my academic role. Although I'm a division chief, I do my job. I have NIH funding, I do my job. I'm a physician, I do my job. I'm a mother, I do my job. But nobody cares about my patent or my companies.
Right. No, and that's exactly what needs to change. And one of the key initiatives in our strategic plan, which is the part you worked on, called the Hemispheric Innovation Hub, is the idea of really developing South Florida as a major hub of innovation, like you have in Silicon Valley or in the Cambridge-Boston corridor and other parts of the United States. And as I was saying before, every one of those successful hubs has a comprehensive research university, and that's the role we have to play. As you know, there's a number of pieces of that. The Launchpad as an educational tool for students and alums to learn more about innovation and entrepreneurship. You spoke about the Converge Miami, a partnership with the Cambridge Innovation Center to actually create this ecosystem with the incubators and accelerators and venture capitalists. It requires building that infrastructure. It very much colored our recruitment of a new provost who's sitting just behind you. We wanted actually a provost who not only understood the upstream excellence in research, which we need in research and in education, but also understood the practice of innovation. And you know, Provost Dirk actually holds about 40 patents himself. And that was a very strong signal about our intention to move in that direction. So in addition to the individual talents like yours, that's my whole point. We in this university, and I would argue in any university that wants to be successful, need to build these structures that actually will support that work. Now that means a lot of cultural change as well. It means changing the way we reward and recognize the work of our faculty members, the rules for promotion, criteria for hiring and promoting faculty. It's a major shift. But we are full of examples of universities that are able to combine excellence and relevance. And have done that to develop that part of the strategic plan.
Thank you. I hope the culture will build faster than the infrastructure, because it's all about the culture, really.
Right.
Yeah, just to add two things, because I've said this over and over again, and Dr. Agrawal mentioned that sometimes you just gotta use that Nike saying, just do it. But it's hard to when you're raising kids, you have a practice and all that. So there's a time in life where you free up a little, where you can do things like that. But somebody has to be the champion, and it's almost a full-time job. I have to do that.
Other comments or?
So actually, maybe picking on Francisco de Caso, I'm associate scientist over at the College of Engineering in civil. We're mostly civil all the time, but picking on the question that was before, if you think about it, education, so kind of looking at the education on the fundamentals, right? We're a university after all. It's the only process or product or service that has evolved small in the last 150 years of modern education, right? University, you go for 4 years, what you learn on year one, not very useful by the end of your graduation. And today there's many ways of learning through MOOCs and online, and MIT provides you everything that you need for free online, right? So all the knowledge that we need is out there. So the question is, given that we haven't innovated the way that we deliver this sort of, becoming innovators and, all those sort of things, what risks do we face as a university, as a research university? And what should we be doing with industry partners, with, junior faculty and with senior faculty that we're not doing, so we can leverage on all these wonderful opportunities that we have, but we're missing? So, risks. Thank you.
Well, you do touch on I mean, we've been talking about innovation stemming from research, but education itself is a field that's experiencing very rapid innovation. In fact, for whatever reason, education was one of the very few fields that did not experience a technological revolution in the 20th century. I mean, compared to medicine or to transport or almost every other field. We basically have been operating with the original innovation of the Gutenberg printing press. I mean, because even PowerPoint is just another way of displaying printed words. And that innovation, that technological revolution is happening now. So another aspect of this and why the Circle of Knowledge is truly an integrated process is innovation around education itself, which, by the way, can also lead to startups and all kinds of the way we deliver innovation and technologies in the way we deliver education. But also, if you build, that's one aspect of the connection. But the other aspect is if you create this innovation ecosystem, you also provide educational opportunities for students. Because the one thing we know now is the classical paradigm that you first learn theory and then you apply it in practice is not the way humans learn. And you just said, I mean, you learn something on year one. By the time you graduate and you need actually to be applying that original knowledge is probably obsolete. Humans learn much more through immersive processes that then they are, and it's our role to then create an educational environment where they can process and elaborate that into concepts and theories. And it's a two-way dialogue rather than this unidirectional paradigm of learning the theory and then applying it. And I think if a university is part of an innovation ecosystem, any of the experiences you've heard would offer right now opportunities for students to be immersed in the actual process of innovating, of developing new technologies. And that then creates I mean, this is the way we actually educate scientists. You put them in the lab. You make them actually do it. Well, the same thing applies to engineers, to any other set of students. So education does come in as a topic of innovation in itself, and new technologies. You mentioned the MOOCs. And also as a part of building the innovation ecosystem and using that ecosystem to then enhance the educational experience of the students and the learning outcomes of students by offering them immersion opportunities.
Yeah, I mean, just to build on that, I really agree that massive participation of undergraduates in research is really happening a lot more. And, you know, I get contacted by prospective University of Chicago students wanting to know if they can get something started in their freshman year and things like that. I'll also put in a plug for our northern Chicago neighbor at Northwestern. They've been doing interesting things for a long time. They've had a program there for a long time called Engineering First, which means you don't wait until you've learned all the chemistry and physics and biology and mathematics, but you start talking about engineering problems from year one. And our friend Julio Otino won the Gordon Prize last year for thinking about whole brain engineering, which really brings other elements of creativity into thinking about engineering education. So I think there are innovations. There certainly are risks too, though. I'm not trying to diminish that.
Yeah. I mean, a particularly interesting example is the rise of simulators. We just built an entire hospital here at the School of Nursing. It's a simulation hospital. It is very high tech, but it's fundamentally an educational instrument. And that's an example of education in itself as an object for innovation. And a place where you pull together other areas of innovation to feed the educational mission. The circle is, in good universities, which is what we are striving to be, the circle is fully integrated. You don't have research here, education here, innovation over here, healthcare over there. You actually have a continuous, mutually enriching process between those elements of the circle, or what I call the circle of knowledge, but that process of production, reproduction, recreation, translation, and utilization of knowledge.
Please.
Please.
Yes, thank you. I am Professor Delgado Almeida from the Clinical Research Unit in Valencia, Venezuela. And we discovered several advanced aspects from cardiology, specifically about the arrhythmia, cardiac arrhythmia. Then we developed a novel method to reverse ventricular fibrillation and other arrhythmia. Ventricular fibrillation because it's at the top, you know. And the second is the treatment of heart failure from grade 1 to grade 4. And then this is the screener is very clear. And then I have the opportunity to talk with you, and then I call you, with your offices. It's not what is important is that you or other physician or research from other university just to support our investigation. But this investigation is completely, it's not just to advance too much. But the reversion of ventricular fibrillation is in every people with treatment. And heart failure is reversed virtually in all people. And that's not, it's not lesson for any people. It's not a discussion, it's not a proposal, it's some are facts, that I can talk with you, we can call you just with your office just here in the University of Miami, excuse me. And I will be delighted just to share all this investigation that is completed, just as writing, I am writing the article, and it's a big advance. Thank you. Bye.
Thank you. Please.
That's fine. What do you think are the biggest legal barriers to your research?
Is that a question to the
Yeah.
three panelists? Any
If
legal?
there are any, I'm assuming.
Yeah.
Experimenting in humans without FDA approval.
Small problem.
I mean, the regulatory environment is a challenging one, and lots of things die along that path.
Well, yeah, I think I maybe was a little too quick there, but the regulatory aspect is very important. You really have to show it works before you can try it in people, and you don't know if it works until you try it in people.
That's the whole point of I mean, at least with drugs, right? That of your own work. And there was, somebody else had asked for the floor, and then we will wrap up.
Hi, my name is Alyssa Bostavanos. I'm a neuroscience major here, and I'm a senior. I'm actually here with one of my best friends, who's a mechanical engineering major, and I brought him because I found out about this conference, and I said, wow, this is a great thing. I don't think I'm going to understand half of it. You're going to not understand half of it. Why don't we come together and figure this out? But essentially, what we were talking about up there is this culture that you guys are trying to create with faculty, and how you're trying to bridge, I guess, engineering and medicine and bring it all together and think differently in each way. And how do you get students like us to think in both ways? And we just want to know, how are we going to produce a culture of students that are going to become the future one day, who are going to think like people like you?
You come and immerse yourself in some of the activities. I guess the easiest thing is to come to our group meetings. That's just for me. Anyone's welcome to attend our group meetings, and we talk about these issues at lab meetings. Welcome to attend those, for sure.
I mean, in many ways, engineering is more like medicine than either of them are like science. Both are consumers of science. So, I think, but I think what you're sort of talking about is taking the first step. How do you get over the initial hurdle of getting into those environments? And I think it's sort of a tried and true way. University faculty are eager to deal with individual students. We don't all just like to go in there and talk for 50 minutes and leave. So I think I would suggest that every student really try to use the university that she or he is in for their own purposes, and not necessarily in standard ways. The faculty is there really to serve you. So
I think it's important to do a research project so you can get your name out on publications. It also kind of tells you what you're really going to have to do in real life if you work somewhere. And then the rest is an evolution. It's I think we're all in your shoes at one time, not knowing what's yonder, beyond the horizon. But you learn, and then you make connections. And actually, publications is the way to make connections too. because you can stand at a poster and you can talk to people. So it's a process, but there's a light at the end of the tunnel.
Thank you.
Thank you.
This was a great comment, and actually on the same line, I want the university to be slightly more proactive. So I work at the Diabetes Research Institute. I am a scientist, I deal with stem cells, and a few years back, actually a few months back, I had the luck to have a bioengineer in my lab who had a slightly different way of thinking and see things. He was very young, he's actually sitting right here, Harold. Hey. So one day, after a discussion, he came up with an idea. He developed a very serious ideas that could be applied. He developed an instrument that could measure certain fluorescent proteins in just a couple of days. He came to the lab, and he started testing it with me and people around me, and I was blown away. So I said, this is amazing. How can we implement this? So I started searching on the university website for funding for young investigators, like undergrads, and that could, help in developing these ideas slightly further, just to see if it has potential, because it seemed to me. And there was no such thing, at least if it was there, I couldn't find it. So in other universities, University of North Carolina, Chapel Hill, in the region of the Research Triangle, I've heard of these competitions for ideas and build something new. And they're, somehow peer-reviewed, and they make like very serious science, and they develop things. They make something really innovative, partnership of, engineering and medicine. I think something like this should be started here. Let me know.
Yes?
Hey, sí.
This is Celia Barber, Chair of Biochemistry and Molecular Biology, as well as Associate Director of the Biomedical Nanotechnology Institute. And I've been sitting here and hearing, and I didn't want to cut in, but we do a lot of things that are very interdisciplinary for our undergraduate students, for our graduate students, and we promote a lot of innovation and entrepreneurship at the educational level and at the research level. We do have an NSF-funded program, interdisciplinary, between the College of Arts and Sciences and the College of Medicine. I'm the co-director of that program, PI, as well. And we foster exactly what you were talking about, like how do we come together, engineers and scientists and medical researchers. So it's exactly that, because in our program, although engineering is not part of it, we also allow faculty from biomedical engineering to have students in the program. Actually, you had a student last year. So this is one of the things we do. We also have created a path for students that graduate with a PhD to give them the possibility that to get an MBA in only 1 year after they graduate. Okay? So we have that component as well. We also have another program where we have scientists in industry working with scientists here at the university and mentors to get a PhD in biochemistry and molecular biology, having joint advisors in the company and in our department. Networking between our students and the students in the companies happens all the time. So we have a lot of programs where we're promoting that. We have workshops for our graduate students in conjunction with the Office of Innovation, and Dr. Norma Kenyon is a champion of that. She's a wonderful director of innovation, and she's done a tremendous job here. And I have a slightly different experience than what Dr. Fornoni talked about. And I think that, we just need to perhaps publicize it a little bit more. Maybe that is the problem, but we have a lot of programs at all levels to foster innovation. And, our students go to competitions in innovation. One of my students just got an award for a young innovator at the TRICOM conference in molecular diagnostics in San Francisco, which is the largest one. So we do promote It's just that I think that people need to perhaps be a little bit more aware. But I think that UM is doing a fantastic job. I came here 8 years ago, and from 8 years ago to now, it's totally night and day. We have a huge number of startups now. They were almost none at the time when I came, and there are a lot of licensing. And I wish that Dr. Kenyon would be here now to actually give you the numbers. But you know, there are things to be said for how we are moving forward, and we have a new provost that is very much into that for as well. So,
And thank you for your comments. And thank you to the panel for a provocative, intriguing panel. I'd now like to ask for a rising vote, cane vote of thanks to our presenters and President Frank. Thank you. We'd also like to thank NAE President Moat and NAE Home Secretary Jane Henney for sponsoring this joint symposium. Given the interest, we'd like to suggest that the two academies redo this, but not too quickly here. With that, we can adjourn. We have a reception that has been set up at the Finker-Frankel Family Promenade. You can reach that outside the building to the right. There'll be UM staff help us in directing. So you leave at the rear and it goes to the right. Follow the assistants who will be directing you. Again, thank everybody for your attendance.